Thank you, Fernando, and I'd like to start by thanking the organizers for the opportunity to be here back in beautiful Brazil. So this talk is about what we call gluon saturation, colored glass condensate, and I'll try to emphasize some of the latest developments in the sense of precision calculations, which in this context will be next to leading order corrections. All right, so okay, so it works. So a brief outline. As you know, there was supposed to be a talk before me, and that was also saturation related. So that was unfortunately canceled. So I did a bit of rearranging. So I'll do a quick introduction to what gluon saturation is, mostly hand waving, and then argue that that requires a new framework in which to calculate things. And then the latest, in a sense, the state of the development of the approach, and that's where the main part of the talk will be. And then I'll also argue, very important, that Electron-Ion Collider is going to provide us with a very unique opportunity in which to study a very interesting region of QCD. So let's get started. So what's saturation? The idea is very old, and just about 40 years ago, Grubov, Levin, Rishkin wrote this very pioneering paper. They argued that if you consider radiation of gluons, because of, as you go to very high energies, there will be large phase space available, longitudinal phase space. And if you have phase space available, you will radiate. And if you consider radiation of all these gluons into some fixed transverse area, at some point you'll end up with a very, call it a dense state of gluons, system of gluons. So this is called saturation. So they argued that the hadron at super high energies becomes a dense state of gluons, a state with a large occupancy number. Now, it's also important to realize that one can reach a dense state of gluons in a nucleus at a much lower energy, so presumably much cheaper. And nuclei are friends in this context. So that's the rough idea of a saturation. Now, apparently it was a surprise, a pleasant surprise, that when they measured parton distributions at Hera, they realized that they are growing very fast with X. Now, we all know X is the fraction of the momentum or energy of a hadron carried by a parton. So a lot of the C quarks, but predominantly gluons. So for this talk, we'll assume that hadron or nucleus is all glue and practically nothing else. So, of course, the question is, where does this come from? And this could be understood from PQCD itself, that if we look at what we refer to as splitting functions, probabilities to radiate, these are dominated by the case when a gluon is radiated. And it favors basically radiation of soft gluons. So soft in this context means longitudinal momentum being very small. So if this is the case and you have phase space, you will radiate and eventually populate your hadrons. And in this particular kinematics, in the so-called double log, you can show analytically that the distribution function grows very fast. Now, of course, this raises the interesting possibility that in this limit, one could be opening up, in a sense, a new kinematic region of QCD, where very interesting dynamics is happening, which would not be visible in the standard high PT limit. So that is the, in a sense, reason to study this. So this is my hand-waving description of saturation. As you go to high energy or small x, and I will use these words interchangeably, eventually your hadron or nucleus becomes a system populated with gluons. And at some point, this idea of a quasi-free parton by Feynman breaks down. It's not a useful concept. You really have to think of it as one collective object. And at this point, one can try to see at what sort of scale this happens. So at what momentum scale this phenomena happens. So you can kind of wave your hands and introduce this packing factor basically number of gluons per some unit area times some scattering cross-section. When the probability the left-hand side becomes order 1, you say you have reached the saturation region. Okay. Now, from here, waving your hands again, you can basically get an estimate at what momentum scale this should become important. That momentum scale is called the saturation scale. It's a q-squared at which this relation is satisfied. That saturation scale, in principle, you can see that it will depend on momentum fraction x. In principle, this will depend on the geometry of the target, so impact parameter, how far from the center you are. And luckily for us, it will also depend on the nucleon number. And LK showed this in her talk. For a large nucleus, small x gluons have very large longitudinal wavelengths. It will overlap the full length of the nucleus. So it can be enhanced by as much as a to the 1/3. Now, the power dependence, the dependence on x, that power you see, it's a number which is calculated from first principle in this context. And it's quite precise. It's better than next to leading order. It's actually some next to leading order. So to me, that's the most robust aspect of this formalism, the x dependence of observables, or equivalently rapidity dependence or energy dependence. Now, if you really reach this dense system, then the standard PQCD approach cannot be valid, which is based on basically the idea of a single parton from a projectile or target participating in a scattering. One really has to worry about this whole thing as one object. So we would like to do that, and there are reasons for doing it. You basically want to understand QCD in this new kinematics, where you think if like things happen that would not be visible to the standard PQCD in the standard PQCD kinematics. In other words, how do correlation functions of your QCD observables basically behave or evolve in this dense region? How do you get there? Maybe there are some scaling laws and so on. There are some theory questions in principle one could ask. There are also practical reasons to study this. And this has been done very much so in the context of heavy ion collisions. For example, people use these as initial conditions for the evolution of the quark-gluon plasma that one forms in high-energy heavy ion collisions. One can study questions such as whether the produced partons, gluons, will thermalize, what are their properties, are there long-range correlations, and so on. So there are also practical reasons to study this. And also the last one is usually called nuclear shadowing, and this approach can also be used to study that. So that's a brief introduction to saturation. Now, I argued that at high energy or small x, your proton or nucleus is a very dense state of gluons, and collinear factorization, the called standard PQCD approach, cannot be valid there. Then what do you do? So you need a new formalism. And this new formalism is what's usually just called color glass condensate formalism or gluon saturation formalism. So Larry McLaren and Raju Venugopalan came up with this new approach. Remember, the idea of saturation is pretty old, but they wrote down some effective action way of treating this. And there's a very nice intuitive picture of kind of realizing the idea. They said if I take a very large nucleus and look at some transverse size, which is much smaller than the confinement size, so I'm not sensitive to confinement, and then I'll look at this nucleus along the beam direction or longitudinal direction. Now I'm going to see a large number of nucleons overlapping, so I will see each nucleon having certain number of gluons and other things. I will see a large number of gluons in this little transverse area. And they said, well, the idea of a quasi-free parton is not good, so what I'm going to do is basically introduce what they called color charges. Basically anything, any quark, gluon, whatever is sitting at large x, and for reference, you can imagine x is larger than 10 to the minus 2 being called large x, less than 10 to the minus 2 being called small x. Anything that is sitting at large x, they called color charge density rho. Now, this color charge density will have some distribution on the transverse plane. So there's some transverse profile. And since the hadron is moving super fast, it's right on the light cone practically, then it is a delta function along the longitudinal direction. So those are the color charges, the large X effective degrees of freedom. And if you have a color charge, it will radiate. In this context, these color charges will radiate me a classical gluon field. So in other words, if I solve the classical Yang-Mills equation subject to this current, which has one large component, I can solve it and find the classical solution to Yang-Mills equation. The classical solution in light cone gauge is actually pretty complicated. It is given in terms of a two-dimensional field, which is related to the color charge densities. Despite its appearance, it cannot be inverted. So it's actually good to go away from the light cone gauge and work in the so-called wrong light cone gauge, where life becomes simple. But this is the idea. This is the generalization of a tree-level PQCD process to this dense environment. Rather than dealing with individual partons, you treat the target proton or nucleus as being represented by a classical color field. So it collectively radiated by those large X color charges. And that is the, in a sense, the tree-level or classical level approach to this formalism. Your target is a classical color field. Any scattering in this context involves projectile objects scattering from this classical color field. So that is what you do. Imagine you have a dilute proton scattering on this dense proton or a dense nucleus. So you can think of as a forward rapidity process. Now, if you take a quark, for example, from a dilute projectile and scatter it on the dense target, this is going right through the nucleus. I drew it outside to make it more clear. It's going right through the nucleus. Nucleus now being a dense object, the projectile will undergo multiple scattering. If you have a large density, you will have multiple scattering. Each scattering is as important as the first one. Now, the problem with multiple scattering is that in color theory, it is hard to sum, impossible, unless you make approximations. So the dominant approximation, the most common one, is the Eikenel approximation, where the energy of the incoming guy is assumed to be so high that it will exchange a little bit of transverse momentum with the target, but stay on a straight line. Small angle deflection, the standard Eikenel approximation. This sort of a multiple scattering can be resummed very nicely, and the relevant part is this basically non-abelian phase written as a Wilson line. It resums all the multiple scattering from the classical field of the target represented by this field. Now, all these guys are collectively drawn as this big, thick, black object representing the target. So whenever you see this sort of a thing, it means multiple scattering is included. So in this dense environment, a classical calculation, or tree-level, if you wish, calculation, involves these Wilson lines that resum multiple scattering. So in this context, these are our effective degrees of freedom. Rather than having individual quarks and gluons in the collinear factorized type approach, we have these Wilson lines as our starting point. An observable such as a cross-section, for example, the simplest case, will be given in terms of correlation functions of these Wilson lines. In this case, the simplest possible thing, amplitude quark going through the target involves a Wilson line at transverse coordinate x-perp. Remember, stays on a straight line, so x-perp does not change during this propagation. You square it, then you get the dagger, Wilson dagger. You can think of it also as an anti-quark. So the correlation function is of this Wilson dagger, and that's the simplest object we have. We call that a dipole. So this is the simplest ingredient of the physical observable in this formalism. If you wanted to recover the standard PQCD limit, you would have to expand these guys. The single scattering limit you can recover, and that's back to small x limit of PQCD. All right, so this is a simple thing. Now, that is a classical or analog of a tree-level calculation where you scatter partons on partons and PQCD. The next step would be to do a one-loop correction to it, and that's where, in the context of collinear factorization, your DGLAP evolution comes in. In this case, we are interested in the high energy limit. So, of course, we also need to do a one-loop calculation involving radiation of gluons predominantly. We are working in the small x limit, so the radiation is favoring the case when the radiation has a very soft or small longitudinal momentum. In this limit where the longitudinal momentum of the radiation is small compared to the parent guy, the vertex simplifies. It's a very simple expression, and it's useful to write it in coordinate space, in which it basically becomes the polarization vector of the gluon dotted with the transverse separation of the radiated gluon with the parent quark. So you'll see that the radiation kernel will involve factors like this. Now, in principle, you will have virtual corrections, you will have real corrections. So let me briefly walk you through this. So I mentioned that the tree level or the leading order process is basically giving you a dipole, a quark, anti-quark pair, if you wish. There's a quark line going through the target at location x perp. Here's, if you think of it as an anti-quark going through the target at location y perp, that's my starting point. Then I do one radiation. Virtual correction could involve a gluon radiated by the quark line, absorbed by the same quark line before they go through the target. Only quark, anti-quark go through the target. Same thing, except the radiated glue will be absorbed by the anti-quark. So these sort of diagrams topologically leave the dipole as a dipole. Or you could have real corrections, for example, like this, when a quark will radiate a glue. Now the quark anti-quark gluon system, the three of them will go through the target, and then gluon will be absorbed by the quark line, or gluon will be absorbed by the anti-quark line. Following the color lines, these sort of things will break up your initial dipole into two dipoles, or dipole squared. So this, the correlator of the Wilson lines, the dipole is basically what we call the S matrix, or the other version, the T matrix, 1 minus S. So you can sum up all these diagrams, and this gives you a very nice equation for how a dipole, a quark anti-quark dipole, will evolve with one radiation. This d dy is the rapidity. Think of it as log of x. How does my dipole evolve with rapidity or small x? It evolves by radiation of a gluon. And gluon at large NC is basically a quark anti-quark. So you can think of this as I start with a quark anti-quark dipole. One of them radiates a gluon. Gluon is a QQ bar itself. Now I pick up two dipoles. It's possible that one of the dipoles will scatter from the target, or the other dipole scattered from the target. None of them scatters from the target, or both of them scatter from the target. So this last part, the nonlinear part, is the most interesting part, and that's the relevant as part in the dense system. If you have a dense system, then both will scatter. The linear part, the first three terms, you are probably familiar with BFKL physics. The first three parts are really the BFKL equation. So this famous equation, BK equation, is extremely, it looks very nice, it's very compact, but it has a lot in it. So all these objects, the T matrix, the dipoles, contain all the dynamics of the dense target. So it's essential we understand how they behave, how they evolve either with rapidity or what's their PT dependence. So remember, the observables, production cross-sections, will be given in terms of these dipoles and new degrees of freedom that we'll soon see. So we want to see how these guys behave in momentum space. So if you Fourier transform the solution of this equation to momentum space, in the very high PT limit, you'll see that you'll get the usual 1 over pt to the 4th behavior. That's the 3-level PQCD, partonic. Now, in the very low PT region, remember high MPT in this context means comparing with the saturation scale. Saturation scale is what, in a sense, separates the dilute region from the dense region. So in the high PT region, you're in the very dilute region, the standard parton model. In the very low PT limit, you're in the saturation region, very dense limit. Here you see how the dipole profile changes with PT, very roughly becomes a constant. So you see a significant change in PT dependence as you go from PQCD to this dense region. And this will appear in your production cross-section. So you expect to see a leveling of PT dependence at very low PT. Intermediate region, where PTs are higher than saturation scale, but not much higher, just around the border, then the interesting physics here is this is the BFKL region subject to saturation boundary condition. Here the physics is the physics of small x-ray summation and BFKL anomalous dimension. And you see how this also reduces the PT dependence. So here you also expect cross sections to be modified by this. And I should say that in the language of quarks and using the language of quarks and gluons and PQCD, this is the only way to get leading twist shadowing from using the language of partons. So this sort of a behavior can be used for observables in the context of proton-nucleus collisions or forward proton-proton collisions. Let's say for proton-nucleus collisions, you define a nuclear modification factor, which is basically production cross-section in proton nucleus divided by proton-proton collisions properly normalized. So this sort of a behavior will give you suppression of this in some momentum region, and that's sort of a thing, signature that you look for, of course, quantitatively, how much and so on. And as I mentioned, this can lead to both leading and power suppressed shadowing. All right, so of course, now we understand aspects of the theory. We know how to do a 3-level or classical calculation. We know how to do a 1-loop correction to it. So we get our energy dependence. Now we would like to basically compare quantitatively with observables. Now this sort of a thing can be applied to any collision where you have at least one hadron or nucleus on one side. So the most complicated one being nucleus-nucleus collisions. Here, as you well know, there's a quark-gluon plasma, and there's so much, in a sense, final state stuff going on that what I described, it'll be very, very hard to kind of fish out. So one goes to a slightly simpler case, what we call dilute dense collisions, prototype proton-nucleus collisions in the forward rapidity. Proton will be a dilute object, nucleus will be a dense object. Of course, here you'll still have colored states. Now here, DIS is the simplest possible case. At least one side is nice, electron part is nice. And here one can apply this formalism to inclusive and diffractive structure functions. I won't really talk about that today. I will focus on the dihadron production or dijet production. And there's also a 3-hadron or 3-jet production. So very roughly, the signatures, qualitative signatures that you will have is that classical multiple scattering will lead to PT broadening, and the amount of it will be dictated by your saturation scale. The evolution with X, as you go to forward rapidity or high energy, evolution is important. This sort of a thing generically leads to suppression of PT spectra, or in case of angular correlations, to a reduction of the away side peak. So those are generic predictions, and I'll go through these real quick. These are very old ones, PT spectra, RIC, single inclusive, and double inclusive hadron production. Here, this was a big news when RIC was doing this, and the reason for that is if you look at dihadron correlations, you tag on one hadron, let's say you call that a 0 degree. You look in the opposite direction. In case of a proton-proton collision, you see a nice peak. Partonic level, that's the momentum conservation. And then you do the same thing with deuteron nucleus, and you see the away side peak goes away. So this is the kind of signature that was predicted by saturation physics. There's much newer work using NLO. I won't really bother with these, but this is a state of the latest. And of course, this is a very important result. Again, dihadrons. LK showed this, and here you see proton-proton away side versus aluminum target versus a gold target, and you see the suppression, and that suppression goes away when you move to a larger PT kinematics. And here you see the A dependence versus of the different species, proton-proton versus aluminum and gold. So these are the sort of things that qualitatively were predicted, and there is numerical quantitative results available. And I do want to point out, if you insist on a Gribov-Glauber type model of non-perturbative shadowing alone, that's not going to do this sort of a thing. Saturation will. All right, so one last thing about data. Now, saturation people have argued with non-saturated people forever that whether there is saturation at HERA or not, and most people don't believe it. It's not conclusive, though the best one we've seen is that when people looked at the longitudinal structure functions and with the latest calculations, they saw a tension at the smallest x. It was realized that if you include small x resummation, that discrepancy goes away. So there was a need for small x effects. But take it with a grain of salt. It's still, people are still fighting, and they will keep fighting until the IC comes. All right, so let's move on to the main topic of this talk. So you think of this long part as the introduction. There's been a lot of activity towards precision in this formalism. The part that I will focus on is the inclusive observables, and in particular, dihadron, inclusive dihadron production. A lot of recent work. Another avenue of precision is the calculation of subiconal corrections to go beyond the iconal approximation. And of course, there's a lot of work on fairly, I will not mention anything but diffractive studies and also applications to spin. Very interesting. So now let's get to work. So let's focus on inclusive dihadron production in deep inelastic scattering at small x. Now, the dominant mechanism will depend on your kinematics, whether you're looking at mid-rapidity production or forward rapidity. So if you look at mid-rapidity production, for this you need a large window of rapidity, which basically means a very large energy. In this case, virtual photon splits a QQ bar. You need a lot of, this is the rapidity axis if you wish, you need a lot of room to evolve and form all these ladders. Your produced hadrons could come from different parts of the ladders, either different ladders, same ladder, or ladders different but different rapidities. This sort of a thing has been done, and with leading log accuracy, but not next to leading order. The most common form people are now focusing on is the forward rapidity production. So this is basically along the photon. So in this kinematics, in the forward rapidity kinematics, you have a virtual photon splitting into a QQ bar, and the QQ bar will go through the target. Again, remember this thick thing means multiple scattering. And then you'll produce them, two hadrons. This is the leading order diagram in this kinematics. It's a very simple interpretation. Expression is pretty simple, bunch of Bessels. Bessels basically describe the splitting of a virtual photon into a QQ bar. K0 for longitudinal photons, K1s for transverse photons. The interesting part are these red ones. These S's is what I call the dipoles, the 2-point functions of Wilson lines. And now for the first time, you also have what we call a quadrupole, 4-point function of Wilson lines. And you can see why, because remember each quark or anti-quark line going through the target is described by a Wilson line. That's 1, that's a dagger, you square it to get 4. Some color combinations will reduce it to 2. So you get your target described in terms of 2 universal quantities, dipoles and quadrupoles. And these gentlemen in a very pioneering paper showed with leading NC accuracy, large NC limit, any process you consider in this context will involve only dipoles and quadrupoles. And that's significant. Why? Because of universality. Because the evolution equation, what I refer to as Jim walk, is the same equation that tells you how these guys evolve. The only thing different will be the initial condition will be different, but the evolution equation is the same. So that means any process we consider, we know how we can evolve it with energy or x or rapidity. So this is a leading order calculation. Now, how do you do next to leading order? And this is work done with my former student, Philip Bergabo. So we focused on inclusive dihadrons. There is work done by Farid Salazar and colleagues on next to leading order dijets. And they have done a more sophisticated calculation involving Sudakov suppression and so on. I think Farid is scheduled to give a talk tomorrow, I think. So very interesting. So how do we do this? So again, as usual, there will be real corrections. There will be virtual corrections. The real corrections involve production of 3 partons. So a quark, anti-quark will radiate a gluon. Now, this work done, this was done years ago with, in collaboration with my colleagues, Alejandro Ayala, Martin Henchinsky, and Maria Elena Tejeda-Yeomans. So we considered QQ bar. Then either quark or gluon or anti-quark will radiate a gluon. So there are different topologies. When the QQ bar will scatter from the target, then a quark will radiate a gluon, or anti-quark will radiate a gluon. Or QQ bar, one of them, will radiate the gluon, and the QQ bar gluon will scatter from the target and go on. These are the real corrections. And then there are virtual corrections. Again, what you can do is a QQ bar, a quark radiates a glue, and the QQ bar gluon system goes through the target. Gluon is absorbed by the same quark. This could happen also before going through the target or after going through the target. And the same diagram for anti-quark line. Or one of the quark or anti-quarks will radiate a gluon, and then the system, the 3-parton system, will go through the target, and then the gluon will be absorbed by the other guy. Or the gluon will be radiated by a quark, absorbed by anti-quark, either after QQ bar goes through the target or before QQ bar goes through the target. So these are the virtual diagrams, and as you can imagine in any sort of a calculation, life is hard. Now you don't need to pay any attention. This was just to wake you up maybe. So the only part worth mentioning is that you see the same degrees of freedom, dipoles and quadrupoles. That's all we really need to know from here. And in terms of actual calculations, it's quite complicated, so it's very useful to use new methods. In this case, we use what's referred to as spinor helicity formalism. Very efficient in terms of for doing the Dirac algebra. So as usual, you do this and you get some divergences, and it's essential that you show, just as in PQCD type calculations, your divergences can be handled. So the first class is UV divergences. Real corrections are finite, but the virtual guys have UV divergences. In this context, that happens when the momentum of the radiated glue goes to infinity, or in coordinate space, the coordinate of the radiated glue approaches either the quark or anti-quark, the parent guy. In this case, there are cancellations among various diagrams. For example, in the first line, this diagram, UV part of this cancels UV part of that. Similarly for the other guys. There are soft divergences. That's when the transverse momentum goes to 0 and the momentum fraction goes to 0. Or in coordinate space, when the transverse coordinate of the gluon goes to infinity. And again, there are cancellations among real and virtual diagrams. This is quite standard in PQCD. In this particular case, the soft divergence of this diagram is canceled against soft divergence of that diagram. There are collinear divergences. That's when the radiated guy gets close in angle to the parent guy, but at finite momenta. In this case, what you do is introduce the so-called fragmentation functions. So basically the leading order delta function, the one loop corrections to it, the divergences can be absorbed here into what you call evolution. This is the standard DGLAP evolution of your fragmentation function. So collinear divergences can also be absorbed into, in a sense, renormalization of your fragmentation function. The only thing left is now the rapidity divergence. That's when z, momentum fraction of the radiation, goes to 0, but happening at finite k-perp. In this case, what you do is introduce a factorization scale in rapidity, or in this momentum fraction z, zf, and you break up your integration region into the below that factorization scale and above that scale. Below that scale, you really have a divergence. And that divergence is absorbed into running or Jim-Walk evolution of quadrupoles. Those are the red parts, and dipoles. So in this sense, you can show that the small x divergence or rapidity divergence is absorbed or leads to evolution, x evolution of quadrupoles and dipoles. So all the divergences are taken care of. So in summary, you can write your full result as very hand-wavingly or symbolically as convolution of leading order cross-sections with Jim-Walk evolution in rapidity, or the DGLAP evolution of fragmentation functions, and then the finite parts which are genuinely next to leading order. Now, I'm not showing you any of these terms because they will probably take 20 pages or so, but they are available and can be used for phenomenology. With one caveat, what I have described so far is you produce, let's say in the real case, 3 partons, quark, anti-quark, gluon. What I described here is when you integrate out gluon, you're left with a quark and anti-quark. Now, in case of dihadrons, one will have to consider all possibilities that any of the 3 has to be integrated out. But that's also straightforward. Now, once you have this, you get a bit greedy and realize that, okay, I have this, I can also get single inclusive hadron production exactly from this. How? All I need to do is integrate out one more. And there are good reasons for doing this, because a lot of the complications with dihadrons will go away. Mainly, I mentioned quadrupoles, even though they are under theoretical control, but they make life more complicated. Single inclusive, all you have is the good old dipoles, the same thing that appear in structure functions. So studying single inclusive hadrons in EIC will also be very, very instructive. So this is also done. Conclusions are basically the same, or the process is the same. You start with a leading order process. You produce quark and anti-quark, integrate out one of them. Then you do the next to leading order corrections. When you do this, integrate out one of the final state, guys, you'll see that there is some general cancellation among diagrams. And that comes from unitarity. And anytime you put these 2 lines together, the Wilson lines, of course, will give you 1. There are some general cancellations. There's also, very similar to what I described, cancellation of divergences, almost identical. So you get some final result for the single inclusive hadron production. And here, you can also go ahead and make connections to the physics of TMDs and so on and so forth. So now, let's also go back to what we know about Electron-Ion Collider. So these processes will be studied at the Electron-Ion Collider. But I also want to emphasize, so these figures are from LK and Zhaojuan. Very nice to provide me with these figures, and actually you already saw this one at least. So what's shown here is the production of dihadrons at various energies, the different colors. And here is the range of target gluon x. So gluons of the target carry some fraction x. That's plotted here. And the question is, where does the production cross-section get its contribution from? What range of x's? And you see, depending on the energy level, there's a distribution of x's, and here the average x is pretty high. Now, here no distinction is made in rapidity. If you make it more differential rapidity, you see that mid-rapidity blue line, roughly. As you go to forward rapidity black line, you are kind of pushed into smaller x's of the target as expected. So if you go to very forward rapidity, then you'll be dealing with small x's. But it's important to keep in mind, EIC has a large coverage of target x. If you have a large coverage, one should utilize it. And I would like to argue that this transition region from large x to small x will be probed very precisely in EIC in the channel of dihadrons. Dihadrons will actually be really looking at this sort of a transition. So it's important theory-wise to also understand how this transition happens. Now, what is this transition? It's really going from collinear factorization in PQCD to this sort of a saturation physics. That is not really understood. So let me now move in that direction and try to argue that saturation physics is pretty well understood, at least theoretically, and we'll probe it very precisely in Electron-Ion Collider. But one should really try to utilize the full kinematics of EIC. And for simplicity, I understand there are nuclear effects and stuff at large x, so I'm going to ignore them. I'll assume starting point large x is just standard collinear factorization and deglap and so on. But at the moment, we do not have a formalism that can cover all kinematics. For example, this kinematics is our standard collinear factorized and PQCD kinematics, high PT. This kinematics, when you go to high energy at fixed PT, is the physics of saturation. Each one is pretty well understood, I would say, but however, there's no formalism that can include both collinear factorization at high PT and color glass condensate and saturation physics at low PT or equivalently at small x. That is missing. It would be extremely gratifying, both theory-wise and experimentally, to have this formalism. It will allow you to merge, in a sense, saturation physics with the physics of jets and quark-gluon plasma. It'll allow you to consider energy loss, full coherent or partially coherent. It has implications for interactions of ultra-energy neutrinos. Spin physics, of course, is modified or gets corrections from this, and very interesting stuff. So, but that's a big problem. And since Electron-Ion Collider is 10 years or so away, we have time. So I would argue that it's a very interesting problem to think about, how to unify PQCD and large x physics with the physics of saturation and small x. It is difficult because each one, the starting point is different. PQCD, you have parton scattering on parton. Quantum corrections lead to your deglap evolution. Saturation, you're starting with classical fields. Quantum corrections lead to small x evolution. How would you merge these things? I think in principle it is impossible, but in some sense, in some kinematics, it should be possible. My advisor, PhD advisor, told me, probably true, that any leading log problem in QCD should be solvable, and I think this is that sort of a problem. So here is one sort of approach. Right or wrong, we'll see. But what is the problem with saturation physics at large x? In saturation physics, your target, described by this classical field, has momentum modes which have practically zero longitudinal momentum. All they have is this transverse momenta of order of QS. If you scatter from that, you are not going to get a large deflection. If you come with a very high energy, you exchange transverse momentum of order QS, your center of mass energy is roughly infinite, you stay on a straight line. It's a small angle deflection problem. That is not PQCD. In the parton-parton scattering, you can get scattered backward. So large angle scattering. So how do you merge them? So one idea is saturation requires resummation of all the multiple scatterings, soft scatterings. PQCD has one hard scattering. If you wanted to do all order hard scattering, that's impossible. But at least one can do one hard scattering and as many soft scatterings as you like in CGC. That one hard scattering, and by hard I really mean scattering from a large X gluon, which carries a large longitudinal momentum, you will get PQCD and deglap, collinear factorization. Now, if you include all the Eichel multiple scatterings, you will get saturation. So this is one idea. It requires that You start with scattering. There's supposed to be a target at the bottom here, but this is an exchange from a large X gluon. You require that you have at least one, not at least, but only one large X scattering from a large X gluon of the target. But then you have, in principle, infinitely many soft scatterings from these small X gluons of the target, either before the hard scattering or after, or both before and after. This sort of a hard scattering will deflect the projectile parton by, in principle, can deflected by a large angle. So you're going beyond Eikenall approximation. Looks complicated, but formally can be resummed. So this is our standard Eikenall approximation. Parton comes in, small angle deflection stays on the straight line. Now parton comes in, has infinitely or many soft rescattering. One hard scattering gets deflected, moves in a different angle now, does not stay on a straight line, now it's moving at a different angle, but can still have multiple soft scattering from the target. And then you have to introduce a new frame, in a sense, to resum them into a Wilson line in this new frame. Now the complication comes in because the large X gluon will also interact with the small X gluons, and those actually can also be resummed. And then you also have the possibility of both the large X gluons and the final state quarks interacting with the small X gluons. So you see, if you want to go beyond Eikenall scattering, life becomes hard, but still possible to do. So formal expressions exist for this, and you can show that you get the Eikenall approximation back if you take the, basically get rid of the hard scattering. Now, the chair is looking at me. Okay, that's plenty of time. All right, so this sort of idea now can be put in a more, let's say, a concrete example. But before that, it's important to realize that if you do this, you actually get some stuff, some phenomena that is not present in the standard saturation physics. For example, if you want to get spin asymmetries from saturation, you must go beyond Eikenall scattering. At Eikenall level, there is no asymmetry in saturation, spin asymmetry. So this sort of thing I described, you can show that it leads to spin asymmetry. In this particular case, I consider double spin asymmetry. For heavy ion people, this sort of a thing will lead to what's called baryon transport. Beams are coming in. These are all baryons coming in. Now, standard saturation, they are moving on the light cone. They lose nothing. They stay. Now, in real life, of course, they lose a couple of units of rapidity, for example, at RIC. That's called the beam rapidity loss. You would get that from here because now the projectile will exchange longitudinal momentum with the target and lose its longitudinal momentum. So if you apply this to a very concrete, let's say, example, consider, for example, radiation of a photon. And the context would be to look at photon-hadron correlations. This can be done in the saturation picture, but then you'll limit it to forward rapidity. If you do what I just described, then you can actually consider also forward-backward rapidity. So you kind of generalize the kinematics. All right, so in the Eikenall approximation, sorry for these weird-looking figures, Eikenall approximation, this is your target. You can radiate a photon. A quark will radiate a photon either before hitting the target or after hitting the target. There is no radiation while you're going through the target. That's suppressed in the Eikenall limit by energy factors. Now you want to generalize this and allow basically scattering from the large X gluons of the target. That also means you can scatter and radiate gluons, photons while going through the target. So there are, again, 4 categories of diagrams. A quark comes in, has many soft scatterings from the target, radiates a photon, scatters some more. One hard scattering gets a large deflection, more scatterings. Or the photon will be radiated after the hard scattering. And again, there are different combinations of, and believe it or not, these can also be resummed. So in principle, formal expressions exist for this. And for peace of mind, you can show that these diagrams, when you take the soft limit, basically taking the limit where PTs are high, basically reduced to the standard exact kinematics of 2 to 2, production, parton scattering, and PQCD. You get the quark-gluon scattering as in the standard PQCD. So at least in this limit, you know you're not doing it wrong. So formal expressions exist, but again, this is an analog of a tree-level or a classical calculation. Of course, the next step would be to do a one-loop correction. If you could do that, that would involve radiation of a gluon. And then, as usual, you would pick up all these divergences and you'll have to handle them. And that will, ideally, that would give you a cross-section which contains PQCD with collinear factorization in one limit, high PT limit, and saturation type stuff in the low PT limit. Now, this is a photon. You see how life is complicated. Now imagine a gluon, so life becomes super complicated. So as a first try, question is, do we even understand how to do standard renormalization in the context of CGC? What I mean is, we saw how those dipoles and quadrupoles satisfy this evolution equation, BK or Jim-Walk. That's evolution in rapidity, or small x. Those objects don't have any UV divergences. Unitarity takes care of it. Wilson dagger is 1 as they approach each other. How would you introduce those sort of UV divergence in this context? That's what you need to get your collinear factorization. It is hard, so we said, okay, well, that's too hard. Let's start with a smaller thing or a simpler thing, we thought. My advisor used to say, small steps for small feet. So I said, okay, what's the smallest step you can take? Start with a good old, what's the simplest thing? Take your standard gluon distribution function, standard definition, renormalize it, standard, except do it in the presence of these classical color fields, which are the building blocks of saturation physics. Life becomes very hard very quickly, but and working light cone gauge makes life really miserable. There are so many things that everything that could go wrong goes wrong, but at the end of the day, you can sort it out. And we're basically done. So this is work done with my colleagues, Tolga Altinoluk and Guillaume Boeuf in Poland. So we're almost done, and we think we understand how to do standard renormalization in the presence of these classical color fields. That is the first step. But we have done it in the linear regime for a very particular operator. That's the standard gluonic distribution function. Now the goal is, can we go back and generalize this or extend what we've understood to the case of saturation physics and all-inclusive, all background fields included? All right, since I am out of time, I will just put up the summary that at the moment, we have our good old PQCD-based collinear factorization, which is in the PT going to infinity limit proven for certain processes. Nevertheless, bulk phenomena happens at low PT, and that in this context of PP or PA means small x. It breaks down at that kinematics. Color glass condensator saturation approach is a systematic approach at very small x. Now, how small x has to be depends on kinematics, and we'll probe this. There's strong hints from experiments already, and we'll be probing this very precisely at the Electron-Ion Collider, so there's a lot of activities in that direction, calculation of higher order corrections. Now, of course, this approach breaks down at large x. It does not contain the physics of large x. And one should keep in mind that there's a huge phase space available at BRIC, LHC, and EIC, and it will be a pity if we don't utilize that. So I think it's important to understand and study this transition from large X physics to the physics of saturation and small x. So the procedure I described remains to be seen whether, first of all, we can really do what I just promised, and whether it's actually in a sense, practical in the sense of, is it something that one can use simply? But it has a lot of interesting consequences that are beyond saturation physics in terms of asymmetries, beam rapidity loss, allowing you to consider not just forward, but also backward rapidity correlations, and so on. But I'll have to warn you that there are still, it's a hard problem, a lot of things to clarify and understand, but again, we have 10 years or so there's time. So thank you very much.
Thank you, Jamal, for this very nice talk. We have some time for questions. There, please.
Sorry, I apologize. It's very hard to see back there, so let's move here.
I have a comment about this picture of a flat disk. So if you're working with ordinary Minkowski or instant form time, then that would be accurate. You take an object that's at rest, you boost it, and its length, when boosted, is contracted compared to the proper length. However, if you're working at fixed light front time, the formulas for the Lorentz transforms are a bit different, and this rule is no longer symmetric. You do get length contraction if you boost the object so that its P plus becomes smaller. So in the limit of P plus going to 0, it becomes a flat disk at fixed light front time. But if you boost it to large P plus, then instead of becoming a disk, it becomes elongated.
So that's totally fine. A couple of things. You can, since you're calculating, hopefully, Lorentz invariant quantities, you're allowed to work in any frame you wish. I kind of moved back and forth between frames without really warning you. So in this case, we are in this so-called infinite momentum frame. In the next one, I'm in the target rest frame. So I kind of went back and forth. But I'm calculating a Lorentz invariant quantity, and I can do it in either frame. And second part is what I described here. All these things that I described can be done, have been done in light front quantization. And actually, if I do it in the canonical quantization or whatever and use my spinor helicity formalism, the results are identical. Everything I described here, the photon wave function production has been done using light front quantization, identical. So there's no difference in either case. The calculated things are Lorentz invariant. Now this, what I described, is a historical picture, and it's a very nice hand-waving picture, if you wish. But the bottom line is, what is it you're calculating? Is it Lorentz invariant, and you're doing it consistently? And everything I described, structure functions, single inclusive, double inclusive, have been done by my colleagues using light front quantization, exactly as you said, fixed X plus, identical. So hand-waving pictures are nice, very intuitive, but intuitive pictures may not be Lorentz invariant. So at least my intuition is not. But they're nice. It gives you a hand-waving way of understanding things.
So I have one question and one comment. Maybe you can comment on the comment. On one of your slides early on, you had these 4 items that were some kind of approximations that you were saying hadronization is absorbed in something, and there were 4 items on that.
Oh, you mean divergences?
There you go. Oh, sure. Go back.
Oh, sorry.
Go back.
You mean this?
No. There was a list of 4 items where you said that some of the corrections cancel.
Oh, I see. Yeah, I mean divergences. Yep.
Yeah, so I'm amazed that when you say that the first 2, they were,
You mean this?
exactly,
Yep.
ultraviolet and soft, they actually, you say cancel. Is that a perfect statement, or, I mean, is there something simple about understanding why they would cancel exactly? Is something that you can justify?
Oh, that.
Or is just a fact of,
well, hopefully we are doing QCD, which is a renormalizable theory. If I did something and divergences didn't cancel, I would be in deep, as Larry would say, deep doo-doo.
Yeah.
But so this is, in a sense, at least I'm not doing something wrong. So you expect this cancellation, and that, remember the soft divergence cancellation to real virtual, that's a deep statement. That's right.
Okay.
So
And
this
on-
just means I'm not doing something wrong, obvious,
Okay.
clearly wrong. So this is self-consistent.
Okay. And then the last slide, summary slide, where you looked at connections going, yeah, that one here. What I feel is, I mean, the CGC, as my experimentalist view, was invented to study or to understand what happens at low X, the gluon dominated region. And you're trying to connect it to high X, which is a right thing to do, because it should be a very natural transition from high X to low X, or low X to high X, however you want to do it. But that statement, it breaks down at high PT as large X. Is it necessary right now? Because we don't know the full extent of the CGC behavior or the low X behavior. Is it worth trying it now? As an experimentalist, I would like to identify regions of phase space where that formalism anyone could claim can defend to work. I would want to study that first and then see if the transition from high X, which is much more understood, can be made, right? I feel that you're going into a rush. Are you rushing this? Maybe maybe it takes 10 years to do this, and that's why you're starting this now. But I'm trying to understand, what is your motivation?
Very good.
Because that really makes a statement, or at least people who at first glance, who are skeptical about CGC, have a very different takeaway message from that statement. And that's why I'm trying to understand what makes your...
Since I'm surrounded by friends and family, I'll also say that CGC is not a religion yet, so one should be skeptical, of course. And I wish I had a slide. I thought about including it, and I do really mean this. And you pointed out a very important point, that you want to basically establish CGC at small x before wondering about other things. What I argue, and I have a slide not here, but I'm happy to show anyone, it's actually in my other talks or publications, that most of what we know about CGC so far for nuclei, here people are still fighting, that's hopeless. What we know so far is from RIC, forward rapidity, and now LHC, but really RIC forward. If I had that slide, I would show you that the kinematics of forward production at RIC is poorly understood. In other words, if you ask me, what is the target X, gluon X, contributing to this cross-section for producing a pion in forward rapidity PA at RIC? Saturation would give you a result, would tell you the average target X is roughly several times 10 to the minus 4. Collider factorization would give you an answer which is roughly 10 to the minus 2. If you do the same for PP, now there are no nuclear effects in PP. PP, standard PP. Let's say both camps fit the PP data in forward. Collider factorization tells me target X is 10 to the minus 2. Saturation tells me target X is 10 to the minus 4. Both cannot be right. Both could be wrong, but both cannot be right. We don't understand that simple thing. So when you say, I want to establish saturation, I'm going to argue, and I argue this privately, that I don't believe you're going to do that unless you're at super high energy or small x. Then there's no contamination from large x. At finite energy such as RIC, EIC even, I think you saw the dihadrons, right? You're getting a large contribution from large x. You cannot focus on small x alone. Let's look at this. This is forward EIC. Mm-hmm. To me, this means half of my cross-section is coming from large x. It could very well be, and keep in mind, when you want to say establish saturation, it's an approximation. You would like to see where it is valid. If it's a good approximation, you should also see where it breaks down, where it's supposed to break down. Do we have the full kinematic coverage to do that with dihadrons? I don't think so. So in my conclusion, I know my saturation colleagues think I'm being too harsh, but my personal opinion, and of course most of my colleagues would disagree, I think we need this, even to establish saturation. Probably a politically incorrect thing to say, but you know, why do I care? I'm going to retire in a day or two, so I run away.
Thanks, Jamal, for the very nice presentation. It seems that the CGC formalism relies on the large NC approximation. Is there any progress in the 1/NC correction?
So that's large NC. Oops, large NC is commonly used. BK equation that I described is a large NC approximation, but subleading NC corrections do exist. Actually, that June-Walk equation I mentioned contains these subleading NC corrections. And for some processes, they have been calculated. For example, one common place, heavy ion people came up with these long-range rapidity correlations, and then the question was, long-range rapidity means very, very early times based on causality, saturation. In saturation picture, you can get those long-range rapidity correlations, but it's a subleading NC effect. So it is contained in saturation, but most people, numerically, turns out to be small for most processes, so people tend to ignore it. I'm not sure. Normally, it should be 1/NC squared suppressed. That's 10%, but it's actually numerically it's even smaller. But it is contained in saturation. It's not necessarily leading NC. That particular dipole equation I showed is a large NC limit. Yes.
So thank you for that very inspiring talk. And I'm also close to retirement, so I can ask whatever I like.
Exactly.
So I
Right.
enjoy now.
And then we run away.
Yeah. So I'm just curious if this color glass condensate appears already in the state or the proton or any hadron, pion. If we can think as a sum of an infinitely many Fock components that of your hadron, I mean, in the null plane, or and when you go to very small x and look to the one body density of gluon, can we see already in the state of a hadron this color glass condensate?
I totally believe so, and I mentioned I'm skeptical, but to me, the best signature so far, so I don't want to be unfair to my saturation colleagues because, where is it? Oops. The signature that we saw from Rick, to me, there is no, like for example, this one. This was a genuine prediction before data. Has a very natural explanation in terms of saturation physics. This means your target nucleus, in this case, in the language of Fock space, the cross-section is dominated by the highest component kinematically available, which is many, many gluon state. So to me, if you ask me, this is evidence for saturation. I don't really need precision studies. I believe this. All the nuclear shadow, the standard nuclear shadowing people with Gribov, Glauber, you can try as hard as you want. Good luck with this. So to me, this is very good evidence for presence of saturation physics in proton-gold collisions. Proton-proton collisions, of course, saturation scale is a lot smaller. So then we don't have the Hera is subject to debate, but to me, this is a golden channel and this is evidence of saturation. My personal opinion, saturation is already observed. We just need to understand the kinematics in which it's applicable. It is in this kinematics, where does it break down? A good approximation should break down where it's not valid. So this one, you can try to get combining two things. What I refer to as the nuclear shadowing, which means you take your nuclear structure function, reduce it by some amount, we call that nuclear shadowing, That alone will not do this because it reduces both peaks at the same time. What you can do, and this is forward rapidity, and that's one of the uncertainties, is to include what we refer to as cold matter energy loss. In principle, people don't know how to do this in combined with saturation, with standard shadowing. What they did is by hand modify the spectra by hand, shift it, and that kind of mimics cold matter energy loss. If you do that and combine it with reducing your structure functions, then you can do that, yes. The procedure I described, including large X, would allow you to do that from first principle. It will include cold matter energy loss, partially coherent. So despite what I may have come across, I think this, to me, is a very good evidence of saturation.
Thank you very much. I'm sorry to interrupt the discussion, but we have to move on. Let's thank Jamal again. Thank you.
Okay. Should I start? Okay. Okay. Good morning. And first of all, I want to thank the organizers for the invitation. It's not my first time in Brazil, but it's always a pleasure to be here. So today I'm going to talk about the Jefferson Lab in the EIC era and show you how this lab can complement what EIC is planning to do. And in some cases, also how the results that we can have from Jefferson Lab can help to a better interpretation of what EIC will say and will produce. So this is my introductory slide. And for this, I want to quote this gentleman, Nobel laureate, who said that the ability to reduce everything to simple fundamental laws doesn't imply the ability to start from those laws and reconstruct the universe. Indeed, this is, you know very well, this is an asymmetric path. We know that quarks and gluons are in the heart of the matter, but if you want to go from quark and gluon and reconstruct the emergence of the hadron structures and the dynamics, the quark-gluon dynamics, in the case where quarks and gluons are bound states, it's very difficult. We have incredible challenges to do this. And is exactly in this region where Jefferson Lab sits. Now, we know that we have help from lattice QCD, and indeed in the last years, we had remarkable results from lattice QCD, starting from the, here is the spectrum of the hadron, low mass hadrons, the contribution to the proton spin divided by quarks, gluons, angular momentum. So incredible achievement. However, currently there is no formulation of lattice QCD that allows us to simulate the real-time dynamics of a quark-gluon system. And in addition, we know very well that lattice is computationally intensive. So we need experiment, we need the data, we don't need, it's not enough to have simulated data, we want real data, and this is what Jefferson Lab wants to provide. So Jefferson Lab is a lab who wants to explore the fundamental nature of confined states of quark and gluons in the non-perturbative regime of QCD. So this is an aerial view of the accelerator site. And let me describe a little bit what we have here. First of all, is a lab in the US, in Virginia, and it's a DOE lab. And what you see in this picture is the structure, the underlying structure of the accelerator. The accelerator is very simple. We have 2 Linux, 5 recirculating arcs, which links the two Linux, electrons. This is a continuous electron beam accelerator facility, CBAF. Circulate 5 times, and we get the maximum energy of 12 GeV. This beam is highly polarized, 90% of the polarization we have, and can be sent simultaneously to 4 experimental holes. Here you see A, B, C, and D. Not much fantasy for this hole, but this is what it is. And very important thing is that we run a Jefferson Lab experiment at the luminosity frontier. We can run experiment at 10 to the 39 per centimeter square per second. So very, very high intensity. These 4 holes has 4 different detectors, very much complementary, let's say. In all B and D, we have large acceptance detectors. This is the class 12 and the GlueX. And in all A and all C, we have more conventional spectrometers, smaller acceptance, but much higher resolution. And because of the incredible quality and intensity of the beam, at Jefferson Lab, we run also experiment to search, to discover evidence for physics beyond the standard model. We run experiment of parity violating deep inelastic scattering. Now, to probe the emergency of the hadron structure, the dynamics of quark and gluons, is not a simple task. You realize this is a complex problem which demands different approaches and measurement to access multiple observables. It's not that with just one measurement you understand. And indeed, what we do at Jefferson Lab, we study different aspects of the hadron structure. We study this structure of the nucleon and the nuclei, 1-dimensional and 3-dimensional. We do measurement of spectroscopy and hadronization, and also, as I said, test of standard models. This pie chart tells you a little bit how all these physics topics are apportioned. So the biggest part is the study of 1D and 3D nucleon structure. And this is, you don't have to read this table, but this to show you that this 12 GeV program has already started. We had so far 90 approved experiments. We ran 1/3 of them. And we have in 8 years, we will complete mostly 85% of our program. But every year we have the PAC. So every year there are other proposals submitted and additional experiments. So we are busy. We know what, we have a program and we are busy with our program. Anyhow, and here in these slides, I want to show the complementarity at a glance between Jefferson Lab and the AC. So CBAF sits mainly in the region of the valence region, large X. EAC is the detector, is the experiment, is the facility which will study the glue that binds all of us. So it's mainly focused on the gluon part. And also in terms of center of mass energy and luminosity, center of mass energy for EAC is much higher than for JLab. No question, you can see here in this slide. But luminosity is 4 or 5 order of magnitude lower than Jefferson Lab. Now, that said, we want to move to the next step. Even if we are busy, we have a program, but we are looking at the future and in which way we can give another, a more powerful tool to this lab. And we are thinking about doubling the energy of the accelerator and also having a positron beam, but at 12 GeV, not at 2 times the energy that we have now. So and this, as I will show in my in my next slides, doubling the energy is a quite simple task. I mean, we don't have to change the footprint of the accelerator, and I will show in which way the really recent advance in accelerator technology can help us in this. So why we want to double the energy? And in my next slides, I want to show what higher energy can, in which way higher energy can enrich the program that we have. And I will show just a couple of examples, no more, and I will flash on other 2, 3 items. But we are developing now a white paper to describe the physics that we can reach with the 22 GeV. So what a 22 GeV upgrade will bring mainly? There are 2 main points here that I wanted to highlight. First of all, we'll cross a threshold, the charm threshold. We are at 12 GeV, we are really at the threshold of measuring, accessing the charm quark of the standard sector. With the 22 GeV, we will really be able to explore and study, and you will see with the high luminosity what we can achieve. And also, in terms of study, for instance, of nuclear matter, we can reach distances which help us, or we can achieve a distance in terms of R, internuclear distances below 1 Fermi, which is the actual distance that we can probe now with the 12 GeV. And this means that we can access the repulsive nuclear core. And also, very important, in my opinion, is that there is a bridge, we can fill a gap between what we have now, 12 GeV, JLab at 12 GeV, and ESC, even if ESC, the lower the center of mass energy is 20, so we can, in a certain sense, fill this gap. And this is very important because we can test, can give us the opportunity to test the validation of our theory from lower to high energy and with high precision. And in a certain sense, this was also pointed out in the previous talk that we had. So we are developing this program in this way. We just started 1 year ago when we knew that this opportunity to double the energy with a really an incredible, powerful tool that now it seems that we have in hand. So we organized several workshops at Jefferson Lab internationally. We summarized this in a very short booklet now, 15 pages that we have sent to the long-range plan of the writing committee of the long-range plan. Now in the US is under discussion the long-range plan of the nuclear physics for the next 7 years. We are writing a longer document that we plan to submit to archive by the end of this month. And from this, as I said, and all these physics topics that we are discussing and we explored are summarized here. This was the physics topics that we touched and discussed during our last workshop at Jefferson Lab. So this is the physics of JLab. Now, just to give you a feeling of what is possible to reach and how we can advance our understanding of hadron physics if you go to higher energy. And I want to start with the spectroscopy. As I said, if we go from 1 GeV to 22 GeV, really we can explore the charm sector of the standard model. And in particular, we can study tetraquark and pentaquarks with very high precision. And this also, studying the charm sectors will give us also, as I will show you, is a unique method to probe the structure of the proton, as we can link the structure of some particle that we can produce, JPSI for instance, to the gluon content of the proton. Now, About the tetraquark, these so-called XYZ states. They've been discovered almost, the first one, it was, if I remember well, in 2003, so already 20 years ago, but, and they were observed in a plus minus, BDK, but still the nature is, of these states is controversial. There is not a consensus about the content of this tetraquark. And mainly the reason is because if, for instance, I produce one of these ZC, let's say, in E plus E minus, I can produce, indeed, E plus E minus, ZC, pi plus, but I also, and then this is a signature of this state. But I also can produce my final states, pi plus, pi minus, J psi, can come from a creation of D1 bar, D star, one of the DDK, rescattered with the other, and for certain center of mass energy, in the final state, I can have an invariant mass at the energy of the peak of the ZC. So these two mechanisms is difficult to disentangle. These XYZ states have never be produced with lepton beams. So photon or electrons, virtual, real or virtual photons. And what is the big advantages if I use this photon beam? Is that there is not, I can get rid of this rescattering effect. And I can, this can be a direct probe of the ZC, which goes to J psi pi coupling without the scattering effect. And one thing that I want to tell you is that indeed this photo production tool has been already used at Jefferson Lab to prove the existence of the lambda pentaquark that was discovered by at LHCb. So we use this, we produce the, try to produce the pentaquark in the S channel, and we couldn't find any signature. So if we increase the energy, we can use this line on investigation to extend to the other exotic candidates. And here are the projection, and I tell you that this projection are made using the Monte Carlo that we are using now to analyze our data. This is from OLD, the GlueX experiment. This is what these data, the black data, are what they measure for the J psi. The yellow is the projection with the 22 GeV beam, and those other line with the high precision data is what we can have for the XIC, for instance, of the or the psi to S. Now, the complementarity with the IC with this study. ZC, we have, according to the JPAC projection for the cross-section, the production of the Z shoots up at the threshold. But we cannot reach, for instance, Y, because Y is much higher energy, and this is, we need the EIC in order to study this particle. Also, the flux, you see the photon flux, real and virtual, the comparison between 22 GeV and EIC at 5 times 100 GeV combination. We have a much higher flux, but it stops here at 6, 7 GeV center of mass, while EIC can cover a much higher spectrum. So the other thing, we made a simulation. As I said, we have a simulation of we have our Monte Carlo that we use to analyze our data, to publish our data. And indeed, we are able to reconstruct. And this is another important thing that I didn't say at the beginning. What we are planning is to have this upgrade without touching the existing detector in the detectors in the experimental hall. So we'll just touch the energy, increase the energy of the accelerator by using the same equipment that we have. So we can run the simulation using what we have and say, okay, these are results that I'm going to have. And to show you why it's important to have very precise data, here is what GlueX already measured for the cross-section of the J psi cross-section. Total cross-section and differential cross-section, the sigma over the p. The total cross-section versus the energy of the photon, you see that there is a dip here in the, there is this unclear behavior of the cross-section. It's not a smooth behavior. And this is just at the threshold, we see this threshold, this structure at the threshold of the lambda CD star production. Same strange thing is the sigma over the T. These are three different slides in energy. The lowest energy, there is a decrease with the T of the sigma over the T cross section, but then there is a rise. What does it mean? That you cannot this behavior cannot be explained by the T channel only. And T channel means the gluon exchange. And if you want to use the J-psi photoproduction to investigate the structure of the proton, this means to link this data to the gluon GPDs, to the mass radius of the proton, anomalous contribution to the proton mass. Some assumption on the theory has been done, and mainly this assumption is the two-gluon exchange. So it's very important to have precise data in order that the theory can be checked and made the correct assumption when we extract then the observables. Now, same here, you see here, this behavior, for instance, can be interpreted as a possible evidence for a S-channel resonance, which combine with the T channel. We need precise data. And this is indeed what, if you go to 22 GeV, this is the precision that we can reach, not only for the J-psi, but also for other charmed particles. And one important thing to notice is that already at 17 GeV, we can have this one. If we increase the energy at 17 GeV, reach the 17, so we have already this possibility for the J-psi. The other important tools that we have in OLD, we have a real photon beam, and this real photon beam is linearly polarized. So the polarization, of course, is a huge and very important tool in order to understand the reaction mechanism. And you see how this is the linear polarization. The black curves is what we have now at 12 GeV. And this pink and red is what we have if we goes to higher energy. 17 GeV, 22 GeV, so there is almost an order of magnitude increase the polarization. And this means that we can measure the naturality of this particle, and so understand and see if it's a two-gluon exchange, for instance, or three-gluon exchange. And so far, what we have is this one. This black point is what we can measure now with the 12 GeV. We cannot, the error bar is too big in order to do this kind of analysis. Other important topics is the 3D. We have discussed yesterday a lot about this 3D imaging of the nucleon. Is the next step of hadron physics in order to understand the internal structure of the nucleon. So far, we had this unidimensional description, and with these, we have our parton distribution functions. And now we have this incredible tool, 3D. We are able to see, for instance, at which x, which is the fractional momentum of the struck quark, fractional momentum with respect to the proton of the struck quark, what is the distribution in KT, the transverse momentum of this quark at a different x. And this is something that comes from an analysis of a study of Bacchetta simulated data. So you can see the possibility. This is a huge possibility. And here I'm talking about the three-dimensional in the momentum space. Of course, there is also three-dimensional, the GPDs in the coordinate space, which is I'm not touching here. So beautiful, but there is no free lunch, unfortunately. What does it mean? That we have to study and measure more, in the cross-section, more structural functions are involved. And each structure function, or each functions which enter into the cross-section is function or more variable. It's not just x and q squared, but there is more variable. So this 3D study brings a complexity in the extraction of these structure functions. And also, the other requirement is that we need really high statistics. And I will show you why. Now, I don't want to scare you with this formula, but my colleagues before me show something even more complex. I just want to tell you what this formula represents. We can access this transverse momentum particle distribution function in one way is to study semi-inclusive deep inelastic scattering. So you have your electron, hits your scatter off a proton, and then in the final states, you detect not only the scattered electron, but also the hadron. And why you want to detect the hadron? Because if you want, it's obvious, you have to measure the transverse momentum of this hadron. If you want to understand the transverse momentum of the quark, you have to measure the transverse momentum of the hadron. So you have the transverse momentum of the hadron, and you have this cross-section is a function of x, q squared, and these two additional variables, which is linked to your hadron, the detected hadron, its transverse momentum, and z, the fractional energy of the virtual photon that it brings. Then the cross-section is a function of, there are several pieces, and this is the cross-section at a leading order. And you have 18 structure functions at leading order. Each pieces of this cross-section is made by one structure function, which is a convolution of distribution and fragmentation functions. There is a modulation in cosine phi or sin phi, and this phi, those are the angles between the scattering plane and the reaction plane, and phi s is the angle between, if you have a transverse polarized target, between the spin of the target and the scattering plane. So you have this modulation, and then you have an epsilon, a piece in front of each of them, which is function of epsilon. Epsilon is the ratio of longitudinal and transverse photon flux. So you need to access each of them in order to have, to understand what does it mean studying a nucleon in 3D. Now, at fixed target and large x, all these structure functions are accessible, we can measure. But if I go to high energy, and this, for instance, epsilon is equal 1, it's obvious that all these terms here that have 1 nano epsilon or square root of this cancel out, you cannot measure. So we have the possibility to measure all of them and to give information about all of them. Other important thing is in this structure function, in this formula, there are two pieces, FUT and FUL, which is the cross-section, which depends on the virtual photon, which has transverse or longitudinal polarization. And usually it is assumed that the ratio between these two is the same as the AS. So longitudinal photon with a longitudinally polarization is more or less 20% of the photon of transversely polarized photon. But this has never been measured in CDs. And what we can do at JLab, we can do this measurement to really measure what is the contribution of longitudinal and transverse, and you can measure what we call the ratio sigma L over sigma T. We have already an approved experiment at 12 GeV, and this is the kinematical plane that we can cover in x q square, is this red. With 22 GeV, we increase a lot. So it's very important to measure this because this ratio, this R value, and is essential also to understand CD multiplicity, for instance, and other important effects like Sievers and Collis effect. More, I am always surprised when I talk about the 3D structure of the nucleon that the people working in this field, usually you see in the presentation, they are mainly focused, continue to be focused on x and q squared. So how far, how down I can go with my x, how high I can go with my q square. So the mindset is still at one dimension, I think. So if you want to measure the three-dimensional, it's very important to have also a range in PT, in the transverse momentum of your hadron. Otherwise, you cannot measure anything. And this gives you a feeling what we can do with the 22 GeV, with the class 12, one of the detector, the measurement. So the luminosity, how is important to have high luminosity, because we can make this analysis in 4 bin. You see, here is x, here is q square, and each of these is a PT versus z. And we have, for each z, 40 points in PT. And really, you can make a multidimensional analysis. Now, to show you why it's important to have a multidimensional analysis, I just bring as an example the analysis that we are currently doing at class. This is a beam spin asymmetry, one of the terms of the cross section, which is supposed to be higher twist. It means that it goes down as 1 over q square. Now, if I measure the asymmetry versus q square and integrate it out all over the variables, x, z, pt, I have a certain trend. And I say, okay, yes, indeed, the asymmetry goes down as a q square. But if I start to analyze this data in bins of xpt, q square, and z, for instance, I see here for this bin in x and bin in pt, the behavior of the asymmetry is quite different. Everybody can hear me when I talk. Okay, fine. Oh, maybe it's too much now. I have to lower my phone. So if I move to semi-inclusive physics to exclusive physics, that is the same. Come on. To exclusive physics, also is very important. This increase in energy is another important tool. Why? because yesterday we talked a lot about the pion form factors and also GPDs. So if we want to apply GPDs, for instance, GPDs formalism, you have to check that indeed you are in the region where you can apply this formalism. And the way to do is to see how the cross-section goes with Q squared. So the longitudinal part scale as Q to the -6, the transverse part scale Q to the -8, and the large Q square should be sigma L much bigger than sigma T. Pion form factor, you rely on, you don't have a pion target, you have to use this Sullivan process we have discussed yesterday, and the cross-section, mainly you can rely the cross-section to the form factor to the longitudinal part of the cross-section. So what is important is to separate this longitudinal and transverse part of the cross-section. And also in Q square, you see here the relevant Q square range when I go from 10 GeV to 22 GeV is a sizable increase. Now, if you go to the pion form factor, and this is, I took this slide from a talk given by this guy at the APS last month, and he was talking about the measurement of pion form factor at 22 GeV and ESC. And this is exactly a slide. So these are the projection for ESC. This is what we plan to measure. Actually, we already took the data for this measurement at 12 GeV, and this is what we can have at 22 GeV. And this is, since the cross-section, the form factor is linked to the longitudinal part of the cross-section, it's important to separate the transverse cross-section to the longitudinal cross-section. At ESC, you can do this through a model. In a GLab, we can measure. So it's an important check then of the model that can be used at ESC at higher energy. More. Yesterday, we talked a lot about this emergence of the hadron mass, and Tobias here gave a lengthy talk, and I asked also a question about what is the difference between his theory and the theory of this guy, for instance, Craig Roberts. Using this theory, we are trying to do some projections for, so the point is the following. The concept is that quark and gluons acquires mass according to their momentum, right? And this theory has been used to describe the form factors, the pion form factors, PDF, and also the electrocoupling of the nucleon excitation, N star. Okay, so since we have a big part of the program at Jefferson Lab in OLB is the study of the nucleon excitation, N star, the so-called N star program. And since this theory is describing well what has been measured about on the gamma P N star electrocoupling, so the idea, and also predict what is this electrocoupling for the resonances that then we measured and we checked that the theory, the prediction of the theory indeed was correct. So the idea is to study the evolution of this gamma P N star at high Q square, and you need a lot of statistics, so high luminosity to do this kind of measurement. And if you do this, indeed, the idea is that you can span part of the hadron mass, which is almost 80%. Now, as I said, this is based on this theory, and but for sure, this N-star program can be expanded to higher energy and to higher Q square. And to do this, we need higher Q square and so higher luminosity. Now, we talked also yesterday about the parton structure and the spin, in which way we can increase our knowledge with the 22 GeV. In terms of the nuclear strangeness, the idea is to access this parton distribution S+, which is S plus S bar PDF, using party-violating dependent elastic scattering. which is very sensitive to this. And we made a simulation using this solid detector that is being, let's say, developed at Jefferson Lab, a new detector to put in one experimental hole. And the GEM group made this exercise and to see what they gain in terms of precision, how much in precision you gain if you increase, if you enlarge your XQ square range. And you see here the improvement. At large X is almost a factor 2. Same thing for the meson structures. These are the available data you have seen already yesterday. Then you have this red point that we plan to measure at 12 GeV. And this is what 22 GeV will give us more. So you extend in the low X range. And this also will be reflecting the improvement in the determination of the parton distribution function of the pion. Last slide that I want to show of the physics is about the nuclear. As I said, we ran a lot of experiments with the nuclei at Jefferson Lab, and we extensively studied this short-range correlation, EMC effect. And the one idea is that with the 22 GeV, we can study the nuclear force and access the core going to this distance. So this is R in Fermi, and this is the distance that we can reach with doubling the energy. In which way? By measuring deep inelastic scattering and measuring this super fast quark. But in order to have, this is the F2 for the deep inelastic scattering, and this is the quasi-elastic contribution. It's important to go to very high Q square, otherwise this quasi-elastic contribution is almost of the same size of the deep inelastic. So you have to go to very high Q square in order to really be sure that you are measuring deep inelastic scattering without a sizable contribution of the quasi-elastic part. Now, as I said, we want to double the energy. How we do, this is CBAF as it is. We don't want to change anything except two things. So we stay with the two Linux, which are the most expensive part in an accelerator. What we want to replace is just these two arcs, which are the arcs in which the electron at higher energy recirculate, with the two FFA magnet, these fixed field alternate gradient magnet. What are these magnets? So we change these, we recirculate not just one time, but 6 times the electron here, and at the end we have the 22 GeV. And we do this without degrading the quality of the beam. Why it's possible now this? Because we have this technology which was checked at C-beta collaboration, and those are permanent magnets. This is really very nice, because for operation of an accelerator to have a permanent magnet, you can imagine how much you save in cost operation. And they are small, like 10 by 10, 80 centimeter long, and in the same string of magnet, you can transport beam of different energies. And here is a visualization of this magnet. One of these balls is a beam of different energy. And now the prototype is under construction. It was proved that it works for at least for 1.5 Tesla. This is at Jefferson Lab now, and we want to test this to check the radiation residence. And is undergoing this work. So the other thing that we have to, I said we have to change two things, the highest energy arcs, and the other thing is the injector. We cannot inject at 120 MeV the electron. We have to inject at 650 MeV. But we are lucky because at Jefferson Lab in the facility, we have also the old free electron laser that now LERF, low energy recovery facility. And we are going to use what they have as for the accelerator, for the injector, what is in the LERF. Then what we have to do is, since the LERF is here and the actual injector here, we have to transport this beam up to here. 10 minutes. Oh, I'm plenty of time. I'm almost there. We have to transport here. So there is some work in the construction work. But the other beautiful things is that we are going to use this accelerator also as the injector for the positron beam, because in parallel we are developing these two ideas, having a positron beam and and doubling the energy at Jefferson Lab. And the positron beam at 12 GeV, as I said, we are not going to higher energy. And people supporting this program, the positron program, is they already wrote a white paper published in APJA. If you want to have a look at this, you are very welcome. One of the main, say, measurement that we want to do is really to experimentally measure this two-photon exchange, which contributes, could be the reason of the discrepancy in the form factors with the two different measurements, proton form factors. And what is the timeline? This is a really rough timeline. First of all, I want to say that this is not in competition with EAC. EAC has the priority. EAC is a project which has approved by DOE as a CD path to follow, funds allocated, and so this is not in competition with EAC. But we are linked in the EAC in terms of schedule. So what we want to do is the following. We start already this R&D and we want to continue the R&D. Actually, we had some funds already for this year from DOE to continue this kind of R&D. And we want to do the upgrade in two phases. The first is the positron beam. Run a certain time. Here you see the positron beam upgrade phase 1 starting 2030. And this, let's say, schedule is linked, of course, to the EAC funding profile. And then run the positron program and then start with the upgrade, phase 2 upgrade. This is here in 2034. So it's a long time. For sure, it's not tomorrow, but we have plenty of things to do. And I think it's important to push and support this program and think about the future of JLab. And this is, you see, less than 10 minutes. Yes, so I will not cut the time for the breakfast. Yeah, no breakfast, coffee break. So conclusions and outlook. Let me read because this is, I think, it's important to read. So understanding the strong interaction dynamics of non-perturbative QCD and how hadrons and nuclei emerge from the fundamental QCD principle is a complex problem, and which demands different approaches and precise measurement of multiple observables. So precision and multiple observables. These are the 2 points. With a fixed target program at the luminosity frontier, large acceptance detector, we have large acceptance detector and also high precision spectrometer. CBAF offers unique opportunity to shed light on the nature of QCD and emergency on the hadron structure. With a CBAF at higher energy, some important thresholds will be crossed, as I show you, and an energy window which sits between JLab at 12 GeV and EAC would be available. And this can provide a unique insight into the non-perturbative QCD dynamics. Also, we are moving forward to develop this positron beam. And a strong science case for this upgrade is emerging and is supported by the lab management and staff and users. And it will complement and enhance the EAC program. And you see that our community, user community is really big. We annually support almost 1,900 users at Jefferson Lab. And with said, thank you very much for your attention. In fact, it's here.
Hi, Leticia. In your course section, longitudinal, you have the dependence of the pion nucleon coupling. You know the too strong dependence or not?
Which
to
one?
extract the form factor, pion form factor.
The pion form factor.
Yes. Then you have some dependence of
yes,
nucleon,
yes.
nucleon.
Yes, indeed. So what I want to say, you measure you check that you are measuring the longitudinal part of the cross section, which is very important. Then, of course, this part here, you have to model in some way, because this is the virtual pion flux. You cannot, you don't have a detector to measure the virtual pion. Yes, I'm very well aware
also,
of this.
with this formula, we extract the pion form factor space-like only, right? And you know some off-shell effects.
Listen, the way to extract the form factor here is there are two ingredients that you have to satisfy. First is that you have to measure the longitudinal part of the cross section. Second is that you have to go to very low T in order to be close to the pion pole. And we already did this measurement at 12 GeV. We know how to do. We cross-check the validity because, as I said, you have to put a theory here, because you don't know what is the coupling of the pion with the nucleon. And in which way you do? You know that there are measurements of the pion form factor, but a very low energy, 0.3 Q square. And it was a direct measurement of the pion electron. It was done at CERN with a 300 GeV beam on the electron of the nuclei and atomic electron. And they measured, but they could go only a very low Q square, 0.3. And for the measurement that we had at we measured at 6 GeV and we measured 12 GeV, we cross-checked the theory with the 0.3 GeV square where there are measurements.
Hi, thank you very much. So having position beam is great, and I would love to see
I
it.
know.
So how would you do with the permanent magnet? So the
No, that's why
Oh.
you stay with the 12 GeV.
Okay.
You cannot
It never
use,
goes to
and
the
no,
new-
otherwise you go, impossible, impossible. That's why I said positron up to 12. And you see from this schedule that we cannot run in the same time frame, high energy positron. You have to do first the program at 12 GeV with the magnet that we have, then installation of the permanent magnet and run the high energy. It's impossible. Actually, it's not impossible. It's possible, but it's very expensive. Which is the same as saying it's impossible.
Yeah, so
Yes.
two questions. So that's the construction time. Is that
Yes.
correct? All these parts. So positron starts construction in
Yes, Abbey,
Yeah.
very rough.
And
As I
then
said, the
34 is the-
priority as ESC, and this is linked to the ESC funding.
Yeah.
You see?
And then the 31 is the 35, 34.
Yes,
is the beginning.
yes,
Okay.
yes,
Yeah, got it.
yes.
I have one physics question.
Yeah.
I have forgotten why you had these polarization curves for the photon in Hall D. You had very stark falls in polarization, almost quantized at different energies. So you went from
You see,
10.2. You had a plot there when you showed
let me,
the polarized program at the beginning of your physics argument. There was a
polarization.
nice plot of for different energies. You had very sharp drops in polarization. Go back. Oh, there you go. There you go.
Yes,
Right.
but it's very simple. Why? This is gluex. They have linearly polarized photon.
Yeah.
And this is the structure of the lattice of your diamond.
Oh, I see. So that. Okay.
Yes, but absolutely, and that's why you have at the threshold. This is exactly the point, Abbey. So if you see here 9 is the threshold of J psi, and you have a drop in the polarization. So you have your big error bars. If you move to higher energy, this drops goes here, and you have plenty of photons. This is the lattice of your diamond. Yeah.
Shortman.
Sharp question.
Yes, about J-psi production.
Yes.
You have the two gluon exchange that you get the gluon distribution, momentum distribution. I'm just wondering if people saw, besides you saw the evidence for lambda C, D star, about the entanglement between these gluons.
They are working on that. I'm not allowed to show what they are.
Okay, with that, we stop here. Thank you very much. And I propose we stop and have a coffee break for 20 minutes, and we'll be back at 11:25. Okay? Okay. Barrieri, and with that, we'll close our morning session. Please, you can start.
Hello to everyone, and thank you to the organizers for having generously invited me here. I'm going to talk about a somewhat older work, which I did with a former master student who then decided to get even more speculative than this and going to be on the standard model physics. Guillermo, it was published in European Physical Journal A. I'll first talk about sort of the experimental situation, and then I'm going to end what I find unsatisfactory about experimental phenomenological consensus of heavy ion physics. Then I will go on a level, I will go in the same direction as Jamal, but in a slightly more the basic thing with the Gribov-Levin-Riskin equation, which is sort of one level up from the colored glass picture. I'll show some results and I'll show some conclusions. I should say, as a disclaimer, that I don't particularly believe that I'm showing this old work, which I don't particularly even believe in myself, in the sense that I'm working on hydrodynamics most of the time. I mean, I have a student present here who works on the hydrodynamic model. However, I do believe that the questions I'm asking are pertinent, or they need to be solved, and they haven't completely been solved yet. And this work has been sort of my attempt to find their solutions. And the reason I'm speaking about this now, even though the work is old and I'm skeptical about it, is because this is the physics opportunities for the EIC conference. And I have a definite experimental EIC signature, which if it will happen, I will give this talk again and again and again. And if it will not happen, then I'll also be happy because I'm working on other things and I like hydrodynamics too. So yeah, so this is sort of my disclaimer. So as a very short detour into philosophy, there are two main mechanisms in science. You have this existing paradigm and you solve puzzles within the paradigm. And this is what most people do as theoretical physicists, at least. And nowadays it's really nice because Bayesian models and machine learning have, to a certain extent, permitted us to automate this stage. You can sort of throw all the existing data into a machine and the machine learning algorithm will optimize your existing paradigm for you. And then there is a sort of infrared level where the number of puzzles that come out become unsustainable, and that's where sort of instead of looking for planet Vulcan, you develop general relativity or something like that, which comes with its new set of puzzles. And this is something that probably computers cannot do. You still need humans. The paradigm in question that I think has a few puzzles, which is certainly the consensus and has a few puzzles associated with it, is that Rick found the perfect fluid. I mean, there are these wonderful coffee mugs, and it was put in the newspapers. And indeed, relativistic hydrodynamics is still the guiding principle to understand soft physics, particularly in heavy ion collisions. And the observable for this is what is usually called V2. Non-central collisions are the initial shape is something like an ellipse. In reality, it's not V2, it's Vn. The non-central shape is something like an ellipse. if the system is sort of a continuum fluid, the subsequent dynamics of this ellipse, just from conservation laws, will be made by pressure gradients, and these pressure gradients will result in anisotropies in momentum, which are measurable, Of course, there's plenty of other mechanisms that give you anisotropy in momentum. Momentum conservation is sort of a biggie. We all believe in it. However, of course, physicists are more sophisticated than this. And there are two issues to be said. The first one is that the collective Vn should be aligned to the axis, which is perpendicular to the impact parameter. And in some experiments, this is directly measurable from spectators. Not in all of them. At the LHC, you cannot directly measure it. But still, it's more trivial. It's more non-trivial than energy momentum conservation, because this thing here appears in 2-particle correlations, 4-particle correlations, 6-particle correlations, and so on and so forth. And we'll come back to this later. This is the same Vn appears in very high cumulants and is independent of the cumulants, which basically means that this Vn is not momentum conservation, but it's really a collective effect. It's really an effect which has to do with the medium moving a certain way. And this is exactly what hydrodynamics predicts. I mean, if the system was a dust, then the momenta, then you would have collisions, and yes, you would have conservation of momenta, but you would have many pairs of mini jets, if you want to call them that, which move in whatever arbitrary direction they do. And this effect goes away for larger systems, while for a fluid, obviously, if the impact parameter goes to 0, this becomes more spherically symmetric, but even then, you have event-by-event fluctuations that give you anisotropies, and these anisotropies would be imprinted in arbitrarily high cumulants. And this is what experimental data sees. And in fact, hydrodynamics works remarkably well, and more importantly, and this is why this sort of became really exciting, is that if you put in, I mean, remember that you have a continuum between, there are two extremes. You have a dust and you have an ideal fluid. And in between the two, you have a viscous fluid. And if you try to fit the fluid with a viscosity, you find that the viscosity is of the order of 1/4 pi or lower. A viscosity with 0 is actually sort of compatible with data. Something above 1/4 pi, you quickly fail in favor from data. And 1/4 pi is the number that you get from an infinitely strongly coupled particular theory that string theorists like. So some people interpreted this as the experimental confirmation of string theory, and it became really excited. And it certainly led to a lot of theoretical developments of relativistic fluid dynamics, which is actually a very positive thing. So this is sort of where it comes from. And why do people like this description? Well, it does fit data, and it does look reasonable. And it is connected to fundamental physics. I worked in hydrodynamics for most of my life, and I like it. And people think that, and basically it's considered as a given. And nowadays, the idea is, let's attach hydrodynamic codes, initial state Monte Carlo with color glass or whatever favorite, your Glauber models or whatever your favorite initial condition model. And let's attach it to a machine learning Bayesian estimator. And then let's throw all the data we have in the world into the machine learning Bayesian estimator. And this thing there will give you everything from the equation of state to bulk viscosity to whatever other transport coefficients you have. So what's wrong with this? My issue is that if you sort of look at forget machine learning and just look at the world data the right way with your eyes, the scaling that you get is a little bit too simple to be described by hydrodynamics in several important ways. By a messy theory like fluctuating nonlinear hydrodynamics with Bayesian initial conditions, and this sort of bugged me. So, I mean, how did people do hydrodynamics before machine learning and before numerical hydrodynamic codes, like in the 19th century? People invented dimensionless numbers because you have a very nice theorem. You have this Buckingham's theorem that basically says that any system of differential equations, including nonlinear ones, can be rewritten in terms of dimensionless parameters. Any system of n differential equations can be written in terms of n minus 1 dimensionless parameters. And indeed, in hydrodynamics is ripe for inventing such parameters. You have the Knudsen number, you have the Reynolds number, you have the Rayleigh number, and so on and so forth. And all these people lived in the 19th century. And there are dimensionless numbers that basically mix macroscopic scales, so like gradients and system sizes, with thermodynamic intensive scales like the speed of sound and so on and so forth. So can we try to apply this in heavy ion collisions? Of course we can. We know that this Vn is approximately proportional to the nth order of eccentricity. Just from dimensional analysis. This is a small dimensionless number. So products of eccentricities are there, but they're suppressed basically by Taylor expansion. So Vn is proportional to epsilon n. Should also be proportional to the speed of sound, which is sort of also a dimensionless number, especially because physics usually depends on the speed of sound squared. Vn is monotonic, so it's proportional to the maximum of Vn is for ideal hydrodynamics. And it can only be suppressed, so the real one is going to be V ideal, 1 minus the Knudsen number. And the Knudsen number is eta over s, which is a dimensionless parameter, multiplied by something like temperature, which is the microscopic scale, and something like the system size. So this is what's known as the Knudsen number. So the formula should be something like this. And finally, the longer the lifetime, the more flow you will have. So the system should also depend on the system size via the lifetime. And the lifetime is characterized by another dimensionless quantity, which is basically the initial time over the freeze-out time, or the freeze-out time over the initial time, which is also depends on, in hydrodynamics, it also depends on the initial temperature over the final temperature, which is something like the multiplicity. And this is what's known as Heisenberg-Levy scaling. You put all these things together, and you actually get a bunch of things which look very different from experimental data. The most obvious one is the fact that you seem to have, this is sort of old experimental data, because unfortunately, all experiments, unfortunately, the LHC really only concentrates on mid-rapidity, and Rick has taken down a lot of experiments which measure away from mid-rapidity, and this is unfortunately sad, so this is sort of pretty old data, but it seems to show that there is limiting fragmentation of V2. And there is absolutely no reason why any of these should have limiting fragmentation if you have a phase transition between an inviscid fluid and a viscous fluid in the middle. So a hadron gas is supposed to have a high eta over s, a quark gluon plasma is supposed to have a low eta over s. Just the scaling with NC will give you a jump of NC squared. So there should be a critical rapidity where the Knudsen number goes up, and this is not seen in data at all. And this is sort of strange. V2 over epsilon versus multiplicity is also simply monotonic. I mean, this thing here just depends on this. There is no dependence on basically the Knudsen number. So that could be, viscosities could be very low. Viscosity could be very low at all energies and system sizes which are seen so far. And it could simply be that this data has big error bars and they're not sensitive to the jumps in viscosity because viscosity is very low and maybe it doesn't change much. However, this starts being weird when the LHC and afterwards Rick started measuring V2 in PA and even PP collisions. And it looks like the observed V2 is just a monotonic dependence on multiplicity. The observed V2 is just a monotonic dependence on multiplicity. In particular, this can be seen very clearly in V3. V2 does change because the eccentricity changes. But V3 is only fluctuations. By symmetry, on average, it's 0, but in every event, it fluctuates. And the fluctuations in PP and AA are comparable. And indeed, V3 in PP and PA and even AA only depends somewhat weakly on multiplicity and doesn't depend on the system size at all. Well, it certainly should depend on the system size via the lifetime. And moreover, if you look at collectivity, I mean, I mentioned cumulants. I mentioned this cumulant issue because it turns out that if you look at collectivity, a system with V2, if you look at collectivity, you have changes in multiplicity, but these changes are entirely attributable to changes in eccentricity. It seems that systems with 50 particles appear to be as collective as systems with thousands of particles. And even when E/S equals 0, thermal fluctuations, if the bare viscosity is 0, thermal fluctuations in an ideal fluid also give you sound waves which continue interacting. I've actually, I mean, I could give a completely separate talk for this stuff, which is irrelevant to this conference, so I won't. But anyway, it's really strange that you have something that looks like an ideal fluid in systems of 50 particles. Because even if the viscosity is very low, if you have 50 particles, you don't have a continuum. You have event-by-event thermal equilibrium fluctuations in number of particles, which should also give you an effective viscosity. Then there is the fact, which in my opinion is sort of really mysterious, that if you plot V2 as a function of PT, here the x-axis is PT, the y-axis is V2, yes, V2 increases with energy. The V2 at low energy is smaller than the V2 in high energy. I mean, this is smaller than V2 in high energy. But it actually turns out, and this is an experimental statement, that the entire increase of V2 is attributable to an increase of the average PT, which presumably depends on the lifetime. Because if you bin V2 by PT, experimental data, which has order of magnitude, 2 orders of magnitude of square root of S, practically lies on top of each other. And this is extremely strange. In rapidity, something similar happens, and actually I will talk about this towards the end of the talk. Hydrodynamics underpredicts V2. So you have a bigger V2 than hydrodynamics, which is supposed to be the maximum, again, in small systems. So why is this a problem? I did not include PT dependence in my numbers because that depends pretty unlinearly on freeze out. But the bottom line is that what happens is that V2 depends on the anisotropies of the freeze-out hypersurface and on the velocity in a way that should be different from momentum bin to momentum bin. And actually, viscous hydro calculations and transport calculation show a systematic independence of V2 on the PT bins, which within error bar is completely absent from experimental data. Within error bar, it's completely absent from experimental data. So you can actually put everything together, and there is this empirical formula that says that Vn of PT is proportional to epsilon n times a universal function of PT. And this universal function seems to change very weakly with energy, rapidity, and system size. It seems to change very weakly with energy, rapidity, and system size. If you integrate this, you will get a change, but this change exactly follows the change in average PT, not the change in V2 in different momentum bins. Hydrodynamics is a nonlinear theory. I mean, this is why we use Bayesian and machine learning. So experimental data should be related to these parameters via a big matrix. And I mean, the point of machine learning is to try to find this matrix precisely. And what data seems to say is that this matrix is remarkably sparse. And there is a paper, there is actually even an analytical solution of V2, sort of a toy model solution by Yoshitaka Hata, George Noronha, Bowen Shao, and myself, that sort of confirms that this matrix in general should be full, while experimental data points to sparseness of this matrix. And finally, last but not least, I was talking about V2 of different particles, V2 of all particles. I was talking about V2 of all particles. If you look at V2 of different particles, all the scalings I talked about break down. But they break down in a way that cancels out if you consider all particles. Now, this is again very unnatural, because V2 of particular V2 of a given particle doesn't depend on its abundance because it's an eccentricity, doesn't depend on its abundance because it's an eccentricity, but it depends on its mass, and flow. So V2, particular V2 of every particle depends on its mass and flow. Particle abundance, of course, to get total V2, you take every particle V2 and normalize it, weigh it by a particle's abundance, relative abundance. And the particle relative abundance depends on the mass and on the chemical potential and on the freeze-out temperature. Chemical potential changes a lot with energy and rapidity. In particular, for low energies, you have a lot of protons. For high energy, you have a lot of pions. So it's very strange. That two seemingly independent things, like the weighted abundance and the relative V2 mass difference, just cancel out to get a universal scaling. And finally, photon V2 is exactly the same as hadron V2. So what do people say about these things? Well, people say that every one of these things has a satisfactory solution. The photon puzzle, because usually photons are contaminated by final state scattering. Small systems is sort of controversial, but there is different mechanisms to produce V2. I mean, the colored glass can also produce a V2 in small systems. And also V2 has the average PT versus energy. I mean, this universal scaling, there are effects there that cancel out. So none of these things is really an argument that killed hydrodynamics, because again, it's a nonlinear theory. There is potentials for things to cancel out. But these scalings are really weird, and their cancellations at least are inelegant. So it kind of would be nice to find a theory where all of these scalings are natural. And in fact, QCD is scalings. And what I find really remarkable is that some of these scalings bear some resemblance to the sort of scalings that got QCD to be generally accepted as the theory of hadrons, like, DGLAP and the running of X, Bjorken scaling. I mean, the fact that X dependence is very strong and Q dependence is very weak. X dependence is very strong. I mean, here you have sort of collinear factorization calculation, but the whole point is these things are a property of the initial state. This thing is the interaction. This thing is the fragmentation. And this way you have scalings which are really nearly universal, in particular in relation to X, which is related to rapidity, of course. It's the logarithm of 1 over X. So let us entertain a completely unorthodox idea that there is some kind of mechanism where Parton distribution functions become strongly azimuthally asymmetric with small x in a way. What does hydrodynamics actually do? Hydrodynamics is a mechanism of taking initial gradients, of taking initial nuclear gradients, which are very small, and blowing them up into momentum gradients and transforming them into momentum gradients. So that's what we need hydrodynamics for. This is where this epsilon n expansion comes from. So can one try to invent from scratch a mechanism that takes the very small gradients and parton distribution functions at high energy due to nuclear effects and blows them up in a way that still follows the gradients, the small nuclear transverse gradients? If one can invent such a thing, then everything I said about V2, and if the dominant V2 mechanism would be such a mechanism, then everything I said about V2 would follow naturally from the sort of scaling that is natural in QCD, like the fact that things depend strongly on X and they depend weakly on Q squared. In fact, there are certainly ways to do it. I mean, the color glass does have an effect, but the problem is that these ways generally go away if the system size is taken to infinity. So if you have an ellipse and you increase the axis of this ellipse in such a way that this ellipse goes bigger, every such microscopic effect, I mean, for example, the color glass, you have these color domains, but the color domain direction, the color domain is fixed by QS and the color domain direction is random. So if you take an ellipse and you similarly increase this ellipse size, you will have infinitely many color domains, and the dominant V2 will be 0 just by cancellation. While the data scaling that I was talking about shows that this doesn't happen. So you have to really invent something new. And of course, structure functions are azimuthally symmetric. You have GPDs and TMDs, which are azimuthally asymmetric, but they depend on particle spin, and they also go away for large nuclei, because large nuclei, which are collided at RIC, are unpolarized. So again, this cannot happen. So what else can we do? Well, I mean, there is this famous plot, which Elke showed in her first talk, where you see the structure functions as being sort of, you take the Wigner distribution between quarks, and then you make either TMDs or impact parameter distributions, and then you integrate out over the transverse degrees of freedom, and you have running. And it's something similar to what you do when you have renormalization group running. And X, as Jamal explained to you in the last lecture, the evolution in X can also be considered to be it can also be considered to be a renormalization group evolution equation. Where these things could fail is if there is a spontaneous symmetry breaking of azimuthal symmetry in some regime. And because of pre-existing nuclear gradients, just like with chiral symmetry, chiral symmetry is broken explicitly by a very small value and spontaneously by a very big value. Actually, I have a plot about this later. You have a spontaneous symmetry breaking, which is big. You have an explicit symmetry breaking, which is small, which makes the cylinder a little bit skewed, and which makes the symmetry a little bit skewed. But of course, the true vacuum is the one which is the skewing parameter of the explicit symmetry breaking, and eventually the vacuum settles here. In the same way, if you consider a big nucleus coming at you at small x, and there is a mechanism to break spontaneously azimuthal symmetry, the small nuclear gradients which break explicitly azimuthal symmetry will be blown up. So one has to invent something like that. So one has to invent something like that. So what can you do? Well, the color glass dynamics, there are experts here, so of course I will not, who know about this a little bit more, who know about this a lot more than me, so I won't say too much. But the color glass dynamics comes from an evolution, comes from a renormalization group equation, where you basically assume that there is a long region where physics is scale independent. You implement the scale independence into the evolution equations, and you get And you get an effective Lagrangian from the running of the Lagrangian parameters. Eventually, for a system of infinite energy and infinitely small x, you get a fixed point which includes iteration effects. That cannot give you spontaneously broken symmetry, because spontaneous symmetry breaking is sort of an infrared thing. But you can go a step back and look at the Gribov-Levin-Riskin equation. There is no renormalization group here yet, and there is a potential, if you just modify these G's to be slightly azimutally asymmetric, you can investigate the stability of this equation, and you can investigate if there are solutions where an azimuthal instability grows. And this is exactly what we sort of did. Actually, there is a very nice physical analogy of the physical effect that we're looking for, which is turbulence in a tap. If you turn on the tap, if you turn on a tap with sort of a small flux of water, if you turn on the tap for a small flux of water, you get a cylindrically symmetric solution. Which looks like this. If you increase the flux, you will have nonlinear configurations of hydrodynamics, and they create turbulence. And turbulence generally breaks azimuthal symmetry, which is why a weak flux in the top and a strong flux looks symmetric, and a strong flux in the top, which looks asymmetric. We are wondering if something similar happens in a nonlinear equation such as this. We're wondering if something similar happens in a linear equation such as this. And one has to note one thing. Here, that turbulence in 2 dimensions and turbulence in 3 dimensions looks very, very, very different in terms of cascades. In 3 dimensions, turbulence, you have Kolmogorov cascades. So systems of large amplitude, small frequency, generally decay into systems of small amplitude, high frequency, and this is how energy gets redistributed. So initially, I mean, this is exactly what happens here. This is a homogeneous system, so the characteristic wave number is small, and the amplitude is big. Here you have lots of little inhomogeneities whose frequency is high, but the amplitude is small. And this is how the thing is broken. But this is, however, 2-dimensional, the GLR evolution equation is not 3 + 1, it's 2 + 1. And 2-dimensional turbulence is very different. 2-dimensional turbulence is very different because there exactly the inverse cascade happens. Things that were high frequency, low amplitude coalesce to become low frequency, high amplitude. This is basically, I mean, this analogy is sort of suspect because this, in hydrodynamics, this has to do with vorticity, because in 2 dimensions, vortices point either up or down. In 3 dimensions, they can point in arbitrary directions. And this is why in 2 dimensions, vortices simply interact and fuse into larger vortices, while in 3 dimensions, the inverse process happens. There is sort of no vorticity here. There is sort of no vorticity here, but there are these things, and instead of q squared, you sort of have 2 different scales like qx and qy, and you can simply investigate the stability of this evolution to small perturbations which are azimuthally symmetric. And this is exactly what we did. And it actually turns out that unstable modes exist. We tried semi-analytical solutions, and it turns out unstable modes exist. How much time do I have? 15 minutes. Thank you very much. So unstable modes definitely exist. And I mean, we've looked at the growth of the unstable modes as a function of x and q. And it turns out that using physical x and q and using physical gradients, the instability of nuclear physics does have enough time to evolve the instability azimuthal gradients, which meet an unstable mode, which sort of start evolving according to an unstable mode, have just about as much time as to come out with an anisotropy that looks like V2. And in fact, in the paper, I didn't put a plot there. In the paper, if you stick this into something like KT factorization, you will have V2, which is compatible with experiment. You will have a V2, which is compatible with experiment. This is a very rough model, which no one believes in. So we didn't take time. I mean, Guillermo successfully defended his master thesis and went on to greater things. So I started working on other things as well, and we did not quantitatively develop this model. Also because we knew that this way of thinking can be definitely experimentally killed or definitely experimentally confirmed at some point. Can be definitely experimentally killed and definitely experimentally confirmed at some point. It has the right scaling. So these guys are nearly independent. They blow up exponentially, and of course, but the linear dependence on epsilon n is maintained. Yeah. It explains photon correlations because what will happen is that the same sort of collective phenomena, if we are right, then the spontaneous breaking of azimuthal symmetry would be entirely an early state, an initial state phenomenon. But it would still be collective in the sense that arbitrary, in the sense that I gave at the beginning. V2 is defined in terms of cumulants, and it can be defined in terms of arbitrary cumulants. So the whole point is it's independent of rapidity, and you have, it's independent of rapidity. I mean, this is what makes V2 collective. It's independent of rapidity. It's made up mostly of these things called ridges, double ridges and triple ridges for V3, double ridges for V2. And it includes correlations of arbitrarily high number of particles separated in large intervals in rapidity. This was found in AA collisions, PA collisions, and PP collisions. If we are right, and this is an initial state effect, because at low x, azimuthal symmetry is broken, you should also see exactly the same collectivity in EA collisions. You should also see exactly the same collectivity in EA collisions. And to my knowledge, there is no credible hydrodynamics model that gives you V2 in EA collisions. So experimentalists actually started looking at it in old HERA data. This was a Quark Matter 2022 presentation by Chuan Sung, and so far they found nothing. So far they found nothing. So at HERA, this does not exist, and what I talked about, you can forget. It's probably wrong. However, HERA was sort of at lower energies. It has lower quality data, so it has lower quality data than what the EIC is going to observe. So I would just like to, just so that we're certain about things, I would encourage the EIC experimentalists to look for collectivity in EIC data. And if you find collectivity in EIC data, if you find Vn defined as ridges and as many particle cumulants, if you find collectivity in EIC data, I will certainly return to this subject. I will certainly return to this subject. If you don't, I won't. Sort of as a postscriptum, because I like hydrodynamics and I still work on hydrodynamics, if I'm wrong and hydrodynamics is true, you still have an interesting connection between EIC data and hydrodynamics via something that here are Pauli and Bohr, and they're trying to do something which is to measure classically the spin of a particle. The particle here is a tippy toy. But of course, they're quantum physicists and spin is classical, so they failed, as you can see. but they tried. But they're also theorists, and theorists are not good at experiments, right? However, this might be possible, not at the EIC, but at RIC polarized runs. Because as we know, as many of you know, the structure of the nucleus is three-dimensional, and it's also correlated with spin. The nucleus is not a sphere. The nucleus is an ellipse whose axes are correlated with the spin direction. And therefore, there should be an extra V2 in polarized P collisions. There should be an extra V2 in polarized PA collisions. And notice that in experimental data, V2 in experiment is underpredicted by hydrodynamics. It might be because initial protons are a lot more elliptical than we thought. And in this case, we will definitely need EIC measurements to look for, we need EIC measurements to look for hydrodynamic predictions in PA collisions. I will not talk about this more because there is a very nice poster by Gabriel, who's sitting in the back. And during the poster session, you can look up details of this thing and ask Gabriel about this. Which brings me to the conclusions. I am actually a hydrodynamicist. I've been devoting several of my years of hydrodynamics, but there are some very non-trivial features in the data which look a little bit weird if you think that hydrodynamics is the dominant connection of V2 at all energies. But there is a very big theoretical barrier because you would need to explain these scalings, you would need to say that everyone is wrong and V2 is not hydrodynamic in origin at all energies and all system sizes. And this is a very big thing to swallow. However, there might be mechanisms in sort of nonlinear evolution equation which have not been explored where such a thing could happen. V2 might be, there is a possibility that azimuthal symmetries is spontaneously broken. And in this case, by nonlinear unstable growing modes, and these azimutally and these nonlinear unstable growing modes could blow up initial nuclear gradients to something like observed V2. And sort of this is at the moment a very hand-waving thing, but if the EIC sees signs of collectivity, it might be time to look at such models seriously. Thank you very much.
Thank you.
Maybe kind of a silly question followed by possibly a crazy question. So in things like non-relativistic quantum mechanics, you can solve for the ground state of the hydrogen atom and you find it to be spherically symmetric.
Yeah.
But if you were to measure the position of the electron using an X-ray, you'd find it to be localized in a particular place. And afterwards, the wave function would be very spherically not symmetric.
Yeah.
So I would imagine that similar things should happen here. Is there a reason that measurement fluctuations can't be responsible for the azimuthal asymmetry you're talking about?
Well, in fact, that's not a silly question. It's a very good question, and it's actually at the heart of some of the things that people think about. Because of course, the initial state is quantum, and hydrodynamics is a classical theory.
Yeah.
And if you believe in hydrodynamics, then what happens is that wave arms, you have many interactions, and any quantum fluctuations all go away, and the initial state is classical.
Yeah.
The spin, there is actually this spin issue here was inspired by Wojtek Florkowski and Wojtek Broniowski, wrote a really nice paper where they suggested measuring V2 in collisions between nuclei of respectively parahelium and orthohelium. Exactly for this reason, because the symmetries of the helium are very different. of parahelium. Fortunately, experimentalists kind of said, no, we cannot do that because we can't make beams of parahelium and orthohelium. But you don't actually need them because the proton is elliptical. So what you are actually saying is sort of similar to hydrodynamic. What you're actually saying sort of goes into the hydrodynamic model.
Okay.
So you have and there quantum fluctuations are irrelevant because the number of particles is many. You see what I mean? I cannot think of a sort of quantum uncertainty-based measurement because also the reaction plane is random, but the reaction plane is also, it's made randomly, but you can measure the reaction plane directly because spectators recoil in a way correlated to the reaction plane. And this is a measurement which some detectors can make, which is very disconnected to central rapidity. And considering that the system is very complicated and open, I cannot think of a scenario where such a thing like the measuring of the spectators also collapses all the cascade of particles produced in mid-rapidity in such a way that it looks like hydrodynamics. So I don't think that could happen.
Would these measurement fluctuations be compatible though with a non-hydrodynamic picture perhaps?
Good question. I mean, the symmetry breaking thing is more of a field theory than quantum mechanics, right? And in field theory, you don't measure states. You measure particle correlations. You measure subcorrelations in a way that kind of leaves this vacuum approximately unchanged, unless you're God observing the Big Bang or something. So I'm skeptical of this. Yeah.
I'm coming. Do you imply, or did you imply that just boosting an object like a proton, you can just by the quantum evolution change the parton distribution so as to produce anisotropies?
Yeah, basically. And I don't find it too, I mean, you know, in this respect, the saturation picture is something similar. You boost something, and just by boosting something, you explore a low X region, and in the low X, very non-trivial things could happen. So why not symmetry breaking?
Okay, I don't know what's first.
Continuing on the spontaneous symmetry breaking, so we would expect then a Goldstone mode. How would it show up here?
Do we expect Goldstone modes in a space-time symmetry breaking in 2 dimensions? I'm not sure. I don't think you would. I mean, they would show, okay, no, you are correct. No, okay, you're good point, actually. I mean, they would show up they would basically show, the Goldstone mode would be a twisting. The Goldstone mode would be a twisting of these Fourier components in X. And yeah, they would show up with, as you continue evolving in X, you would have rotating modes. And these modes wouldn't have a mass, quote unquote. You would have a sort of vertical modes around. And that would be the equivalent of a Goldstone mode. Yeah. If the EIC finds something like this, it would be the next to obvious thing to look at. Yeah.
Okay. I want to ask your opinion. Okay, taking degrees of freedom as a Koch flavor number, and our world is already symmetry broken on nearly 2 flavor. Then such effect on the phase transition of QCD, what is usually they discuss 3 flavors cases, but according to your aspects, what kind of such effect, symmetry breaking in flavor?
Oh, but the degrees of freedom are not the flavor number. They are sort of the particle multiplicity.
But you mentioned the 2 dimensions, 3 dimensions, different behavior of.
Yeah, I mean,
No connection there.
yeah, no, I mean, this equation here is flavor dependent. I mean, the coefficients of this equation are dependent on the number of flavors, sure. The more flavor you have, the less this linear term is important, very roughly, I think. Jamal can correct me.
Is again a curiosity. Is your, I think, slide 49 or 50 that you say small scale hydrodynamic. Yes.
Yeah.
I mean, when you go to very small x, that you have a lot of gluons, you say this can be also represented as a hydrodynamical system within the proton, like the color glass condensate. This is what you mean?
Well, you can use this. This is sort of what you were. This is sort of the previous question. When people say you use color glass as an initial condition, what happens is that you take the color glass wave function, get the number of gluons as a function of x and y, and call this an entropy density or something like this, and feed it into a hydrodynamics calculation. Basically. So yeah, I mean, in a sense, this is where, but the system is quantum. How can you look at it as an initial state of hydrodynamics? Well, sort of the infinite number of initial scatterings collapse the wave function in such a way that the entropy density follows the original wave function, and the rest of the dynamics is classical. How can this work in systems with 50 particles is a good question. Yeah, sure. Sure. No, I know. Well, yeah, but even then, I mean, the proton inside have an infinite number of particles, but they are correlated because the entropy we know what it is. Like we have an upper limit for the entropy. It's the finite number of it's the number of degrees of freedom. The entropy density is sort of the number of degrees of freedom over the initial size. This is sort of the upper limit. And it seems that the degree of collectivity is independent of the degree of the number of degrees of freedom. This is an experimental data point made by CMS by doing these cumulant analysis for different collision systems, right? So, you know, and this is one of these funny things that it's like, how can this work with hydrodynamics? You were at my talk last week where I had a completely different explanation based on hydrodynamics and how this could work. Yeah. So, but we have to keep our options open. Yeah. Elke is, I think, yeah. Yes. Oh God. Yeah, I always forget this. I don't remember. I think negative rapidity is the gold going direction because that's where the highest multiplicity is. Yeah, yeah, exactly. Yeah, yeah. But yeah, no, go ahead. Yeah, I mean, the initial state is sort of a convolution between proton gold. And in fact, at high rapidity, you have, I think, the proton X is at its biggest and the gold is at its smallest. Which might give you a spin, which kind of, Yes. Sure. Well, I mean, the point is that the people who measured this is again something that has a very straightforward experimental datum that if it goes one way, we'll stop working on this, and if it goes another way, we'll continue working on this. Which is in this analysis here, my understanding is that the experimentalist paid no attention to how the proton is polarized. Yeah. If you see that V2 is independent of this, forget about it. If you see that V2 depends on this, we'll continue working on this. Yeah.
Yes. Okay, good.
Okay, so if there are no other questions, let's thank Giorgio again. And Bruno has some announcements.
Okay. So, two things. We're a little bit late today, but I think since we are one talk less today, I think we can safely come back at 2:30 instead of 2 o'clock and have lunch is a holy thing, right? Like in Italy. So we the poster session is, so I really ask you, please respect the students and stay around, stick around, look at them, they worked on it, so do this, please. Another thing, I spoke with Abe yesterday. I'm actually liking that this is becoming almost like a workshop. We have time to discuss, to chat, probably because we also have less participants than earlier editions. But as you know, this poetic series takes place every 18 months, 1.5, not exactly 2 years. So if interested, if there are candidates, we need also a place where we have it next time, right? So if there's anybody amongst you, I mean, some people left already, maybe I should announce it again later. Please think of it and contact us. All right, thank you. Thank you all the speakers. Thank you.